Ready? Okay. All right, good morning, everyone. So we have this morning, this is the last discussion that I'm leading. Seems like I've been doing this a long time, right? So this, I have some notes for the tutorial that we're going to do. We pull them up here just so we can see them. I think you have access to these already. Okay, so here's the notes. These came from Stuart Wright at EDAX. And they just go through step by step how to do things, what the project tree is, how to, everything from opening the data set, doing individual maps, all this, it goes through and gives kind of step by step instructions. So if you've never used OIM analysis before and you want to try something, it's a good set of notes to follow. What I've decided to do today is just first kind of ask people here if you have specific type of questions, specific things you're interested in doing. I remember a couple of questions that I haven't answered from during the last couple of weeks that I can get to and answer those. But tell me if there's things with OIM analysis as far as texture calculations or mapping or using the partition functions, to select certain types of data, any types of thing you have any specific interest in looking at today for the next 2 hours. Okay, so I have nothing coming straight up. So let's, I am going to jump out of these notes though. They're for you as your reference, but I'm not going to be using them a lot. So I have up OIM analysis 7. I believe that's what you have here is OIM analysis 7 or 7.3, something like that. Which I'm not sure exactly which one this is. But you can see up here at top, it says it's running in demonstration mode. So the license that I have on here is running OIM analysis 9. And so when I reinstalled 7, it didn't have the right file, so I'm running in demonstration mode here. And if you have yours will probably say demonstration mode as well as you put it on your laptop and do things. And there's a number of data sets like this data set that I opened, copper, IC, interconnect, integrated circuit interconnect lines. This is one that I've showed a few times. Interesting. Anyway, this is one that I've showed a couple of times that is just one of their demonstration files. Okay, so I'm going to bail out of that since it's giving me trouble. So I'll start off in 7 and we'll talk about a few things. All right, so I usually start with a new data set or just a new project. Click a right mouse, pretty much in anything in here. If you click your right mouse button, then you can get another set of options. So put your mouse in any window, click your right mouse, you'll get a set of options. Here's the data. Maybe we can look at stress corrosion crack. So I open it up, there's the project, there's the data set, so SCC crack is the data set. All data we call the partition. Okay, so this partition right now includes everything. It's not restricting anything. If I click this here, this is IPF quick map, so this will just show an orientation map that comes up plotting everything. Plotting the data here. So if I look at the image quality map for this data set, you can see that there's a crack coming through this. So this is a stress corrosion crack. It's mostly going along grain boundaries. And I don't know on this one. Let me check this. Let me actually create a new partition. And on this partition, I'm going to say, I was going to throw out low confidence data, but on this one, this was collected without confidence index being included, which means it was either a really early version of OIM data collection or it was done from an Oxford or a Brooker system or something else, right, that doesn't use a confidence index. All right, so I'll cancel that. But there are a couple of things I want to show you on this one. I'm going to delete that new partition for now. Okay, so I have the map. I kind of can see where the crack is. If I click on my right mouse and tell it to include grayscale as image quality, so now I have both an orientation map and grayscale, then I can see the crack a little bit better going through there, right? All right, so there's not very many grains here, but we've done this before where we've calculated texture. So click on all data again. These buttons up here are just called quick buttons, and so they give me just a certain set of options. So if I click on quick pull figure, this will show me all the points in the data set for this 001 pull figure. If I click a right mouse button and say properties, I can say let's add an 011. Well, let's add a 111. Kind of the typical ones we look at. A lot of times when people are looking at FCC structures, this is a nickel-based material. A lot of times when people look at FCC structures, they will plot a 111 pole figure, an 002 pole figure, and an 022 pole figure. Why would they plot 002 and 022 instead of 001 and 011? Any thoughts? If you look at calculate the structure factor and look at the selection rules, for diffraction to occur in FCC, it has to be all odd or all even, right? So 001 would never diffract. So if I was doing a pole figure, it would be an 002 pole figure because I wouldn't get diffraction at 001. Now 001 is parallel to 002, and so it doesn't matter as I'm plotting it up from EBSD data. It'll look exactly the same, but some people will label it as an 002 or an 022, just for that reason. Okay, so you start to see a little bit of patterns in here, right? Kind of have a star shape here in the 111 and the 011. So you can start to see some orientation preference. Like I said before, it's relatively few grains, so we really don't have a lot of information on this. One of the things that's interesting to do on a data set like this is to try and look at specifically where the grain boundary crack goes. So the crack is going intergranular. So let's draw grain boundaries on here. So I'm going to tell it to add rotation angle grain boundaries. And if anything's 5 degrees or higher, let's make it let's keep the line black, that's fine. I'll just make it thicker so we can see it good. Okay, so now those boundaries have been drawn in there. You notice in this crack where I have all the bad data, it's drawing a lot of boundaries. So if I ask it to show me a misorientation angle histogram, for example, that's one dimension parameter of the grain boundary. And I usually go 3 to 63 for cubics, and I do 20 bins. So it shows some low angle, a lot of boundaries here, which are going to be the twin boundaries, right? Sigma 3 twin. Although I don't for sure know that by looking at this plot, because all I see is 60 degrees. I don't see that they're rotated about 111. So I'd have to calculate a misorientation distribution for that. But I generally can see what the boundaries are and where they're, or what the distribution of boundaries is. Okay, let's go back to the map we started with. So I'm interested in where this crack is going. Now, this purple grain, it's gone straight through the grain, but a lot of times it's going along grain boundaries. Actually, this one's only going along some of the grain boundaries, right? It's going through the grains quite a bit on this one, which is interesting. Okay, but let's plot where I am going to have the crack going through grain boundaries. So that's what I'm interested in, what's going through the grain boundaries. So what I want to do here is, I'm going to make this smaller a little bit so I can see on the bottom. I'm going to click on the tab at the bottom that says interactive. I'm going to tell it up here that I want to look at grain boundaries. So this is 2 points across a boundary, right? So I'm going to click across the boundary. I'm going to record the data, so I click there to record the data. And then I make sure on this that I'm showing highlighting, which each point I click is going to be black, so let's turn it to red. So every point I click on here is going to look red. Okay. Now over here it's telling me it's going to show color, it's going to show a misorientation plane for the 1 and 2, depending which. So this can be, I could click across a phase boundary potentially. So then I could have 2 different phases, 1 on each side. Or the 2 grains I click on will have different orientation, and so they're going to give me some information on the plane of that. So that's what is over here. If it's a CSL boundary I'm clicking across, it will tell me what CSL it is and how far away it is. And if I want to change this set, I click the right mouse button in here and click Properties, and it gives me a whole list of things I could use to record. All right, so let's look at some places. Let's say this purple grain and this blue grain, it's cracked through there, so we'll click there. So it tells me that's a 58, 59 maybe, 0.2. I did bring my glasses out, so. Problem with my glasses is I have to look here and then I can't see you, so I have to look over the top. So it looks like grandma, you know, doing this. So I guess I'm a grandpa, so that's okay. But all right, 59.2 tells me it's a sigma 3 boundary and it's only 1.6 degrees away from an exact sigma 3 boundary, clicking across there. So that's actually a twin boundary that it's gone through. So that's the twin. This one's a single grain, so we're not going to say that. We're going to pretend like it's gone through that blue one to this green one. So that's a 33-degree rotation, about a 422.15 axis. And since the phase is the same on both sides, it's giving me the orientation the same on the both sides, the misorientation. All right, let's say it's clicking through this one to here. Just grab a few of these. This one looks like a single grain. Let's say it's going through here. Maybe this little yellow one to here, maybe. All right, so these are the boundaries that it's gone through, okay? Now all I've collected here is misorientations. But what I can do if I want to save these is I can come here and I can say add to project. So now it says interactive data that's been added to project. Now I can't map this, right? You see all these buttons are grayed out for mapping. But I can come in here and say let's do a new chart. And it will be a wanted to do a misorientation angle chart. So it has all the textures, so it has done individual points for me. So let me see if I have another option here. Wait just a minute. Okay, so what it's doing is it's giving me only the and this one is giving me only the orientations that I've clicked on instead of the misorientations, which I was trying to show you here. So it doesn't give me an option to do that. It should tell me I could interpret it a certain way, and then it should tell me that, but it's not allowing me to do that. So hopefully in yours it comes up and you're able to say, okay, let's do a misorientation texture or something like this. See, I should be able to calculate a grain boundary texture because it's just misorientations there. All right. So let me show you one more thing with this data set since it's got me messed up here. I'm going to clear this off. And I'm going to tell it that I'm going to color in grains. So now the grains are going to, let's just give them a single color. So these will just be blue grains now. Everything I click on should turn into a blue grain. And I'm just going to click on the grains that are along that crack. I'm being more thorough than I need to be, of course, for demonstration, but okay, just the grains that the crack has passed through. All right, so now I'm going to take this and I'm going to say, let's export. No. Not exporting. We are going to send points to, yep, that's the one. Send points to, so we're going to do highlighted points to a partition. Or we could do highlighted points to a new data set. So in this case, I'm going to send everything I've clicked on to a partition. So there's my new highlighted partition. So now if I click on that orientation map, it should plot only the grains along the crack. So now if I want to look at texture or some specific properties of things going along the crack, I can select those data points out manually, and I have just those that I can look at. Right? Let's open a new data set here. So we will do dual phase titanium. Okay, so you see I have everything in one project. So if I have a project, I have a bunch of different data sets. Maybe I have an undeformed specimen. Here's deformed 10%, 20%, 30%. I'd probably want to keep those all in the same project and analyze them together. Right? In this case, it doesn't make sense to do my dual phase titanium along with the others. I just happen to have them open here. Any questions on something I've done so far? You should be interrupting me if you have questions, by the way, right? Okay.
Sir,
Yes.
is it possible to calculate the fraction of coherent and incoherent ring boundaries?
Correlated and uncorrelated boundaries is the question. So can I calculate the fraction of each? Now what you're talking about is like in a misorientation angle histogram, for example. And if I click on the properties of that, then we have a potential to do an uncorrelated distribution. And typically what we mean by that is let's assume that we know what the texture is, but we don't know if the grains are next to each other. So an uncorrelated distribution means let's take the misorientation of every grain in the data set with every other grain in the data set. Okay, so that's uncorrelated. So if I have this texture, this is the options for the misorientations I have, even if I don't know if the grains are next to each other. Is that what you're talking about, uncorrelated?
I was talking about coherent ring boundaries.
Oh, coherent and incoherent.
incoherent.
I misunderstood the word. Yes. So the question then was I was wrong about that. Instead of correlated and uncorrelated, which you can do, the question was about coherent and incoherent boundaries. So how to define the boundary. So let's bring this up. Let's take our highlighting off and clear all this. Now we're just going to look at, let's look at the lattice, for example. You can see flip around there. Okay, and I'm going to turn off this. Okay, so now we're looking at grain boundaries. So what do we do with the grain boundaries? So if we come into properties, here he said rotation angle grain boundaries that we wanted to look at. If I want to look at twin boundaries, I could come in and say do twin, or I could tell it to do CSL boundaries, for example. And I can add, and I know my twin is going to be a sigma 3 boundary, right? So let's look at sigma 3 boundaries. Let's make the sigma 3 boundaries red, a little bit thick so you can see them. Okay, so this is everything that satisfies the sigma 3 boundary. It doesn't talk whether it's a coherent or an incoherent segment. Now we don't know exactly, remember, from data on a plane whether it's coherent or not. We just know it's consistent with a 1-1-1 plane or not. So there's a few ways we can do that. A really quick way to analyze it is to click this plane traces. So if I click on plane traces, it's telling me under settings, highlighting, and we're going to go to the plane here and highlighting, and I'm going to tell it to show 1-1-1 planes. Okay, so now if I click on a boundary here, it's going to show the 4 1-1-1 planes that are possible, where those plane traces are. And I'll look at these boundaries that are red, and I'll say, is there one of these planes that lines up with that position that I've clicked on? And you can do that on all the different grains and see if those 1-1-1 planes are consistent with the boundary that is there, right? So that's just a quick and easy look at what it is. Erase those. If we come here and go to properties again, under rotation angle, now I'm going to tell it to do reconstructed twins. I'm going to add these, and now it's telling me I want a FCC recrystallization twin, so that's the one I'm going to do. And then it says coherent plane, so we define what the coherent plane is, and then we tell it how far of a deviation we'll accept, right? So let's say we'll accept 10 degrees or something. So that means that plane trace, if it's within 10 degrees, we'll say it's coherent. And 60 degrees, 1-1-1, we're giving a 5-degree misorientation tolerance on that. And then let's draw those as maybe light blue or something like this, aqua. Now it's going to calculate. Thought we did that already. Let's remove this. Okay, so now where it's coherent twins, you're going to have this line, and it's drawn in as a straight line. So let's zoom in and look at these. So it's drawn in and said these are within 10 degrees, how this boundary is drawn up here. That is within 10 degrees of where the actual twin should be. So you can come in here and look at where the coherent and the incoherent parts are. if we zoom out, here's a boundary that's jumping around, so it probably has coherent and incoherent parts, but as it's looking along there, it says that's not within 10 degrees. So it classifies it as incoherent. Okay, that's what you were asking about?
Yes, yes.
Okay. And then here it's telling you, here's the fraction of boundaries between 5 and 65 degrees of the total. It says 83% of the total. Why doesn't it say 100%?
0 to 5 degrees.
Zero to 5 degrees, right? So if you look in the settings here and you go to preferences and maybe maps and grain boundaries, let's check. It says my minimum boundary misorientation is 2 degrees. So it's not 0 to 5 degrees, but it's 2 to 5 degrees. So if I set this at 5 degrees, that should be 100% of the boundaries, or 5 degrees to 65 degrees, right? So that's just in preferences under these settings. So there's a lot of parameters in here that you can go look at. You know, this defines what the coordinate frames are. We've talked about that. If I click on general, there's all kinds of things of, you know, options that I can look at and say, this is what I want. This is how I want the parameters to be different, whatever. Okay, so let's cancel out of there. Anyway, so it gives me the statistics down here. Sigma 3 boundaries, fraction is about 28%. Coherent sigma 3's fraction's about, does that say 16 or 18? 16, okay. All right, that's the question, good. All right, dual phase titanium. Now you see here we have all data as one partition. It automatically creates other partitions. So if we look at properties of this partition, it's saying only alpha titanium, right? The phase is going to be only alpha titanium. And on this one, it's going to say the phase is going to be only beta titanium. So if I click on this one and do an orientation map, it shows me everything. If I click on alpha and then say show me an orientation map, this is just the alpha grains, right? And then this is just the beta grains. So typically if I'm going to calculate a texture or something like that, then I would want to do it in the individual phases. If you come up to the all data and you say let's calculate a texture, it's going to ask which phase you want to do it in, right? So you can do it up in the other one. It's just going to ask you, but it's better to come down here and do it in the individual partitions. All right, now these are pretty good data, but if they're not good data, almost always I'll come in here and I'll tell it throw away low confidence points. So I say throw away everything below 0.1. And in my software, I have it set so the bad data points turn black. That's up here in the settings, right? So I can tell it to be black or white or pink or whatever you want the bad data points. So I've set them black. So it's taken away some of the data. The data didn't look that bad. So what I'll do is I'll come in here and I'll tell it to clean up. And remember, cleanup changes data. But I'm just going to do a grain CI standardization. I'll define the minimum grain size as 5. So all I'm changing is the confidence, right? I'm not changing the actual orientations I measure. Say okay, and then I still have a few black points. But mostly what I've done is remember in the data set, when you do a confidence index standardization, you take the highest confidence index in a grain, so a given set of orientations, and everything that has those same orientations, you make the highest confidence index that's in that grain. So now if you look at the bottom of the screen, look down here where it says CI. See, within that grain, that's a 0.917. I don't know if you can see that up there, but that's 0.917 in that grain. And as I go through the different XY positions, it's all 0.917. So over here is, again, a 0.917. This is a 0.857. But that whole grain then will be the same confidence. Okay. Now, if I look at the alpha titanium map, And then I say, let's throw out low confidence. If I just click confidence and 0.1, then it won't work for me. So these you have to use the Boolean operators. So this is already selected phase. So I have to say phase, alpha titanium, and confidence index 0.1. See, so you can use this to select, you can select out a specific type of grain, a grain size, or you can look only at equiax grains or only at elongated grains. You can look only at crystal orientations that are within 10 degrees of 100. You can look at only high image quality, or, there's a lot of things that you can use to select. Only Schmidt factors that are higher than 0.4, whatever, right? Okay, so I've done alpha titanium and confidence. Say, okay, you've thrown out some points here that were bad data points. This one has already been cleaned up because I cleaned up at the data set level. Right, so that's the data set. This is the individual partition. So when I did the cleanup, I did it at the data set level. So all these are already CIA grain standardization. So if I look at this map, it should also have high confidence everywhere. Okay, good. All right, so that's just kind of partitioning the data to how you want it to look. In this case, let's say, I've got some transformation structure in here. This is dual phase titanium. These big round ones are primary alpha, right? These acicular looking things are transformed, right? They're transform alpha. And so this is transformation structure in these regions. This is primary alpha. So let's say I just want to look at the orientation of primary alpha grains. Okay? What's my options? What would you do to look at just the texture of primary alpha? Somebody just give me some options. Okay, so you do it according to grain size. So if we do this, we can come into these properties. I'm doing that on the partition level, right? So I'm doing alpha titanium, we're going to properties. And now we'll say, let's partition according to grain size. Whoops. I need to say and, partition according to grain size. And we want, here's a grain definition. 5 degrees will be the grain definition, and minimum grain size 5, so that will be the definition. And then we go to the partition. And we'll say, okay, we want only things that are greater than, and we could put in an absolute size. Sometimes I'll calculate here, and it shows me what the overall size is and the average size. Right, so then I can see what the grain size is, the minimum, maximum, and the average. Or we can do it as a percentage. So we can say, let's just keep those that are in the top 10%, something like that. Greater than, and do I do 10% or do I do 90%? I think I'm going to do 90%. 80. Okay, I always have to think, now am I doing greater than, less than? Then I'll select OK. Now it looks like I missed one here maybe. So I've thrown out a couple of grains that I wanted to keep, right? So then I can just go back into properties, and then I can say, here I told it 80%, but actually let's save anything 60% or better. Okay, I think I still missed one, right? So let's drop that down again. Let's go all the way down to 30%. Okay, now I got a couple that I didn't want. Maybe these are transformation. This one I picked up, so maybe I'm going to have to either sacrifice this or include these, right? So let's go up to 40 and see what it does. But you can see the games I'm playing. That's what's important, is just to see what kind of things I'm doing here. Okay, so we were able to keep this one. We got rid of these. This one I think is maybe primary alpha. Let's see. Yeah, that's a kind of a tweener. So let's say this is selecting all the grains, and if I just want to look back and forth on these, or I want to compare them directly, a lot of times what I'll do is I'll say, let's look at all these windows side by side. And then I have a lot of windows open, so I'm going to go through and kill all these windows. Just want these that I want to look at. And I can tile them vertically or horizontally. Okay, so this is a good one. So maybe I've missed this one. This looks like primary alpha. Maybe I got the rest of them. Well, maybe right there, maybe that corner. But pretty much I got the rest of them, right? So this is pretty good. If I'm doing it for statistics, then I would say this is good. I'm happy with this. And then this is only now primary alpha. I haven't changed this name of the partition. So maybe what I should have done is said, let's create a new partition and do this. So I'm going to say primary titanium here, or maybe titanium primary alpha. Maybe I'll do that. And then if I wanted to compare it later with overall, I would come in here and I'd say do a new partition. And we're going to select phase alpha. Okay, so now I have a, and see I label these on my own. Something like this. Okay, so here's the alpha again. Should show everything, yeah. And then here's the one that's just primary alpha. And then you can go in and you can do your texture calculation. Whoops. Assuming we had enough grains again, we don't, but let's assume we have enough. 16, 5 Gaussian, I'm okay with that. We're going to add our pole figures. Yes?
The option you're showing, unique means that there is no rotation. When you have given edit, calculation method, harmonic series expansion, edit option.
Okay, edit. So we're doing harmonic series expansion.
Sample symmetry. That means unique, there is no sample symmetry.
Okay, so the question is on sample symmetry in this. So if you look at this, typically the options are axial, orthotropic, or triclinic. Triclinic is no sample symmetry, right? So we're assuming there's nothing in the sample that is symmetric enough for us to enforce that. So like rolling, we're not saying it's orthotropic, so negative and positive rolling directions are the same. Or negative normal direction, positive normal direction. So we're just saying on this, let's ignore any sample symmetry. Okay, yep, good question. All right, we're using all the points. I say, okay, let's just add a couple of pole figures here. We have the basal plane, and then let's do a in plane, bar 10, something like that. I usually like to look at this one instead, but it doesn't really matter. 112, bar 20. Okay, it's going through the calculation. And then it says there it is, and if I click right mouse, do a new texture plot. Let's plot up these pole figures I looked at. That's what we have. There's only a few grains, and you can just see individually what these few grains are, right? But they're kind of lying along a band along here, which is kind of interesting, okay? So there is some kind of texturing going on that we can see just in these few grains. Now let's say I want to do the same thing with the entire alpha titanium. So I can go in and click and do it, but one thing I can just do is click on this and say copy document. Click on that partition and then just paste that in there. So all the parameters that I've put in are all still there, right? So then I can plop up this, and there's the other pole figures. And maybe slightly different, right? But not much, because the alpha, the primary alpha are the big grains, are the ones that are dominating texture. If I did the other thing on this data set, Let's do this one more thing on this one. So now I'm saying I'm looking at primary alpha, but I'm going to switch that. And I'm going to look at only transformed alpha. So instead of being greater than 40% of the grain size, I'm going to say it should be less than 40%. So these are the grains I'm looking at now, which I can see 2 primary titanium, primary alpha grains I missed, and another one here. But this is the ones that we'll say are not. And then I can look at these orientations. And now it looks quite a bit different than the other one, right? So this is all of the data, all of the orientations, and this is just the transformed alpha. I didn't exactly get it. What if I don't have very many grains and I want to exactly get it? What would you do? Yeah, that was a bad question, wasn't it? I do that on tests sometimes. Ask a question, the students are saying, what's he asking? So let's say I want to specifically identify each of the alpha titanium grains, and I want to make sure I don't miss any. What's my options? Here's all the alpha grains. So if you remember what we did, right at the beginning here, let's say we're going to click on each of them and we're going to turn them white after we click on them. We're going to click on the grain. So this is the grain. So if I click on this grain, it should turn white. Show how, oh, blue, okay. I changed the wrong one. Okay, so we'll turn them all blue. I could change this to white, but so click there, click here. Each of these are my primary alphas. Maybe this one, maybe that one. It's hard to tell. I'm going to leave that because it looks like in a range it should be. This one I want to click on. Okay, so I think I got them all this time, right? So now I do just what I did before. I click on it and I said send points to, highlighted points to partition, right? Or I could say send the non-highlighted points to partition. So all the alpha titanium grains that aren't primary alpha would go to a partition. So if I say highlighted a partition, then there's all my primary alphas up here now. And they're just exactly the ones that I've clicked on, but it throws out all the others, right? So if you have a big data set, it doesn't make sense to go click on 5,000 grains to do that. But if you just have a few you're looking at, you can do it like that. All right. Okay, I opened a data set that I've been playing with recently. Let's see what it's doing to me. It looks like it's done some funky stuff, so I'm going to jump out of this one. I'm going to open. I think I have this only on a flash drive. All right, so this is a wire arc additive manufactured stainless steel. And actually what happened with this one is we started off with a little bit of carbon steel, just low carbon steel, a donut shape, and then we put stainless in the middle, and then we put donut shape again and stainless again. So we went back and forth between stainless and low carbon steel. So this is a structure that's in the center, right? It's like the donut hole that was being manufactured up through the middle. If we look at the orientation map, looks like this. You can see the scale bar is very big. Okay, and I want to analyze what's going on here. As soon as you get this speckled, that means it's probably some bad data, right? So we have a little bit of bad data that's speckled in it. And that's because it's such a big map. It says it is almost 5.5 microns in Y. So it's 2.5 in X and almost 5 microns in Y, or 5 millimeters in Y. So 5 millimeters is pretty long working distance to use a single background corrected EBSD image. But what do you notice from the structure and what do you expect from the structure? So this is the growth direction vertically. Stainless steel, the low carbon steel's on the outside. We don't see that here. So we see a predominant growth direction, right? Now actually this is upside down from where it actually grew. So we had low carbon steel here around the donut and then filled it in with this stainless. So you see some regions that are starting to point over to the side, and that's because they're going on top of a solid. So typically a solidification direction, we would expect a 100 growth direction going in the in the highest thermal gradient direction. But in this case, it's being deposited on top of some corners. So it's coming down on top of that, and the stuff near those corners is pointing in the direction along the interface of the carbon steel. So that's what starts to happen here. So if I look at a pole figure, what would you expect to look like? Let's say we're going to look at a 100 pole figure. A fiber, okay, 100 fiber. Which direction should it be pointing? Should be aligned with the growth direction, right? So if I just click on this, it's going to give me a 100 pole figure, and it should have a lot of points up here, a lot of points down here, and points along the middle. Do you see that? No. Okay. Let's calculate the texture. Okay, so this one is defaulting and giving me 3 pole figures, 3 inverse pole figures. Let's just calculate those. I'm just using the defaults. So let's look at the pole figures, and we don't care about these. We'll remove these. Just look at the 001. Okay, what do you see? Do you see a 001 fiber? Okay, I see an 001 fiber, but it's diffuse. See, that would be the growth direction up here. And this would be the great circle 90 degrees away from that. It's not pointing straight up like we expected. And why would this be diffuse like this? Why would it be spread instead of a nice point? So if they were growing straight up and down, we would expect them all to be lined up in the right direction. But we see them coming off to the side, right? So it's spreading. They're not all completely straight up and down. Some of them are starting to spread. Okay. Why is it not pointing straight up? Due to strain, maybe? Maybe? What's another reason? Maybe we came in at an angle, maybe we're not sure exactly that it's, maybe the maximum thermal gradient actually is coming out a little bit. Maybe when we cut the specimen, we cut it at an angle, right? So maybe this isn't actually, maybe the growth direction isn't perfectly up. Maybe it's coming out of the page a little bit. Now, if we think it's really coming out of the page, one thing we can do is just rotate our data and put it in the right position.
So that means that my A1 will be out of plane.
The A1,
Will be out of plane.
so A1 we usually say is our reference direction. And so it would be straight up and down. But in this case, if we're saying A1 is aligned with the growth direction, it would be tilted in or out of the plane a little bit, right? So let's pretend like we've cut the specimen wrong, something, but we don't want to go back and do another scan, but we want the data to be lined up in the same direction. So you come up to the data set partition level and you say rotate. Now this is just like cleanup, this is cheating, right? So you're changing the data. So you have to know what you're doing, you have to tell people what you're doing in your paper, right? We've cut it funny, so we rotated the data back into the right coordinate frame. Or maybe, you know, we were looking at a rolled sample and the rolled sample is pointing in the transverse direction, so we've rotated it 90 degrees so it's in the right direction, something like that. All right, so I'm going to rotate about this A2 axis, and I'm going to rotate about, this one says 20 degrees, that might be about how much it should rotate to go up there, okay? And I'm going to rotate 3 into 1, so positive rotation, so this 20 degrees might be about right. So I say, okay, let's rotate. These colors changed a little bit, right? Because I'm looking at what's pointing straight out of the plane. I'm not coloring what's going straight up and down. And now if I look at what the pole figure looks like, it recalculated it, so it should change. Yeah, it looks a little more like a 100 fiber, right? We have 100 up here. Maybe it should be rotated a little this way from what we've done, but you know, it's spread enough that it's probably pretty close to what we should be. Maybe we should rotate it up just a little bit more, but it looks pretty good. So I don't recommend that you do this a lot, rotating the data to try and put it in the exact coordinate frame you want. Because sometimes, you know, maybe we just processed it so that it was actually coming out and maybe we've cut the specimen perfectly. But you have to check and make sure that's true. Or you can see on this, you know, this has axial symmetry, it's cylindrical symmetry. And you can see when we come off the exact center line here, it's pointing out to the outside. So maybe we're not on the exact center line where we cut it. So all these are actually pointing towards, you know, one of the sides or the other. Right? Okay.
So this scan was done at very low magnification.
Yes. Yes, this is almost 3 millimeters by almost 6 millimeters.
In one scan it was done.
One scan. Mm-hmm. And that's why you have bad data points. If I come in here and tell it to throw out the bad data points, which usually I do before I calculate texture, because then it's going to recalculate. Every time I do anything, it recalculates the texture all the time. Because the data is changing, right? So now it's recalculating texture again. So now I've thrown out what those data points are, and probably I would clean it up again with the CI standardization. This is kind of what I will typically do. Modify it in place, okay. Calculates texture again, and redraws the map. Okay.
To go to this low magnification, shall we keep the working distance high?
Yeah, so the question is, if you have this kind of magnification where it's really low, then should you work with a high working distance? And in general, that's true. It depends on your phosphor screen exactly, and if you can get sufficient signal on your phosphor screen. And maybe if you don't have that sufficient signal, you should do multiple scans and then stitch them together, or merge is the term we use. Right, merge the data sets. Which I am going to show you an example of here. Okay, any more questions on this one? Okay. So this is the stainless steel that's on the inner part. So now I'm going to open some scans that were near the joint. So I don't remember what I did on that rescan. Let's just look at the raw data here. Okay, so this is the BCC, this is the low carbon steel, this is the austenite in here. So let's do the next data set. So this was 4 zeros, and then I did, or is it 5 zeros and this is 4? Okay. So what I've done is I took a scan at right up against the joint, and you see this is much finer grain. See, that's a 70 micron scale bar, and the other one was a 900 micron scale bar. So this carbon steel is a lot finer structure. And so I took a scan here, and then I took another scan next to it, and then another scan next to that. So typically I would want to put these all together. So let's say I'm going to merge this one, merge, with the next one, which has 4. So it lets me select which one I want to merge it with. If I have a different step size, so I try and do it with that, it will tell me, well, you can merge the data, but it's different step sizes, so you can't map it anymore. So if you're going to do something like this, you have to use the same step size and the same type of a grid.
So, but the data set should be like specifically like beside.
If you're gonna actually make a single map, then I try and overlap just a little bit. So what I do is I'll take and I'll do a scan that's say 450 microns. I'll scan it. I'll move over just with the X setting on the SEM. I'll move over 400 microns and take another 450 micron scan. So I'll overlap by 50 microns and be able to just put those on top of each other. So that's what I'm going to show you here. Let's open this so we can see these data sets a little better. So here's the 2 data sets. And I can grab one and say, how do these fit together? And you can see I'm looking at this little yellow grain, which seems to stop right there. So this yellow grain should be right about there. So I'm going to put it right on top of it, somewhere in here. All right, and then look at my features along that line. They tend to line up pretty good. You see I've shifted down a little bit. And I'm going to say, okay, I like that one. So now it's adding it to a new data set. So now this one, if I click on it, it has both data sets in there, right? But I've done a lot of these, right? So I could do the next one and the next one and the next one. And then I would, I know what I did on this one. I know what I did. Okay, you notice this has only one phase. So I've scanned everything with the same phase, even though this is austenite down there. So hopefully if I tell it to throw out bad data points, that will all go black. I'll go up to 0.2 this time, throw those out. Yeah, so that all goes away. I'll lose some of these others, but mostly it's okay. All right, so this is only the BCC structure. This is only the ferrite. I haven't done anything with rotating texture or anything. What color do you see mostly in here? Maybe blue, right? It looks like a lot of blue in there, which is, you know, I know the answer already, so I'm cheating, but this is BCC. We've put a donut around. What kind of texture would you expect for a solidification texture? Same as you saw in the FCC, right? You would expect a 100 in the growth direction for BCC. So let's look at this texture. So that's the same thing we did before. Do we see a 100 fiber? Maybe. It should be in this direction, right? Because this is the growth direction still, vertical. So we're not seeing too much there. Let me add a 111 to see what we see with the 111, since I saw a lot of blue in the structure. I see a lot of 111. right? Kind of looks like a gamma fiber pointing straight out at me. Now I'm looking at the radial direction, so that was solidified like this. The growth direction was vertical, but it was done kind of in a donut shape, right? So I'm not sure exactly where the solidification direction was, but I don't see a 100 fiber, I see a 111 fiber. So let's calculate it. Let's change the way, let's keep the binning, that's fine. Except now I'm going to add an ODF plot with that, and I'm going to do it 90, 90, 90 like is typical, even though we probably don't have the symmetry that calls for that. But I might have enough grains that I should go to a higher truncation order. Let's just take a look at the texture plots, those 3 that we calculated. All right, so there's maybe a little 001 in there, but I see a lot of 111, right? So there might be kind of a little bit of competing fibers. If I had an 001 fiber, it should be somewhere, and then it should be 90 degrees away from that. 111 I should have there, and I should have 70 degrees away from there. So I see more of the 111 fiber than I do of anything else. The problem with that is there's nothing in solidification that says I should have a 111 fiber. All right, so now you got to think of what's going on. So we looked at some modeling a little bit, and we said, okay, this is a strain energy driven, so it's because of the accommodation strains, right? So we have a hot material, we have a solidification of stainless going inside and then out, sort of going back and forth with the stainless and the low carbon. And that low carbon is really trying to squeeze down in onto the stainless. And it has a higher coefficient of thermal expansion, so it's trying to squeeze more than the stainless is. And so we get a lot of strain, a lot of hoop stress or radial stress, and that seems to be giving us a 111 texture in the radial direction, which I've never seen before in an additively manufactured material. So that's kind of cool. All right. Questions on anything that we've played with? We're at about time for a 5-minute break, so we'll take some questions and then take a break.
So,
Yes.
the donut you have told, so you have took the cross section like this or like this?
Yeah, so he's asking about exactly what we're looking at on this material. So I am kind of cheating by not showing you. So let's see if I have that easy to get to. I just presented it a few weeks ago when I was at the ICATOM meeting, so. Okay, so here is, blow this up. It's still thinking on my side. Okay, there we go. Still thinking. Okay, so carbon steel donut, and then put the stainless in the inside, and then build up the structure like this. And then I don't know if you can see this, but this is how it was sectioned. So sectioned straight down the middle. So when we look at the stainless steel in the center, we're looking right here in the center. And the carbon steel then is on the on the outside perimeter. And I think I blew one up here, yeah. So that's where we're looking there. And then, oh yeah, so I did come right down here on where the low carbon is. And look at that, and you can see how that rotates quite a bit when we're right up next to the low carbon. So, okay, so I did not show that, but the low carbon steel ones are just from where the this is a tooth structure, right, where you build the layers up and down. We're just right on top of one of those stainless teeth, these jagged edges, and moving out from there. So that's what we're seeing. And I've done several of these, and so these are the two we looked at. When I calculated it up, that's the textures we saw. And as you come out here further, you get different type of textures, but still not a growth texture that you would expect. But it changes quite a bit from right up against the stainless to when you go outside of the stainless. But these are all data sets merged together. How many do I have? 6 or 7? 7 it looks like, that are all merged together there. So. Okay, any more questions? That answered your question? Okay.
Is there any periodicity in this texture?
Say that again?
Is there any periodicity in this texture?
Yeah, so that is a super question actually. So the question was, is there a periodicity in the texture?
Because we are looking at layer by layer.
Mm-hmm.
So every layer does this period.
Mm-hmm. Yeah, great question. So I haven't done that much analysis to determine that. It looks like when I'm near the inside of I've looked at 3 different places, and I've seen this 111 fiber right up against the stainless on all of them. So it's possible that as I'm going, because you have the low carbon, you put the stainless on, which bubbles up, and then you put the low carbon on again, so you're getting, kind of different directions that it's hitting as you hit those intersection, those teeth moving back and forth.
You could look on after the outside is
This jig jag.
stainless steel.
Yeah, so whether there's a periodicity, there's something, I mentioned it just briefly when we talked about texture calculation, something called an orientation coherence function, the OCF. And that says, how does your orientation change with the function of position? And actually my entire presentation here was on orientation gradients and how to quantify orientation gradients. And so it's a great question. There's nice mathematical tools to do this. They're not in the software yet. They're pretty complicated analysis right now, but I think it's a great research question to see if that's actually the case or not. Okay. Anybody else?
So to see the periodicity, we have to go from top to bottom, not from like this.
Right. Well, maybe, right? I mean, we don't know how it's periodic. I mean, we could measure, if we're trying to measure an orientation coherence function, we try and do it in all possible vectors, all possible R's, right? And you don't have to stitch the data together to get this information. You just have to know where your scans are relative to each other. So you can do one, 100 microns over and 100 microns over, and they don't have to be stitched together like I showed you. My students love to stitch things, and they'll do 1 million point scans and stick 6 of them together, so it's 6 million points in your scan. And the computer's just, there's smoke coming out of the computer trying to calculate the textures. It takes forever to do it, so smoke doesn't really come out, but it does crash a lot. So you don't need 6 million points to do a texture, but if you're doing a really nice map over a long range and really small data, and you want it to all be stuck together like that, then the students really like that. So I always tell them you don't have to. I know, but it looks so nice. So, go ahead.
The heat will be extracted in the radial direction. The mostly will be extracted in the radial direction.
For the heat,
For the solidification, takes place in powder.
so the weld head, I don't know, I think I showed the weld head here. Yeah, so here's the kind of tandem weld head, right? So you have the stainless wire and you have the mild steel wire, and it's a TIG welding type of an arrangement. So they're coming vertically. So as it's building that structure up, it's doing the carbon steel around the outside, the stainless in the middle. So at least nominally, the solidification direction is vertical. But how it actually happens when you do the donut, I don't know.
The deposition direction is vertical. Modification direction is the direction in which the more heat is extracted. Because outside it is deposited on the base. Outside is air. It is deposited
Right.
in the air.
Right. So the discussion, just for the online, is the discussion is what exactly is the solidification direction. And frankly, I was hoping that the texture would show us that, but the texture is showing us a component that's completely not a solidification texture, right? 111 fiber is not a solidification texture. And so I can't determine from the texture, because what I would say is the interference from the strain effects. So I can't go in and determine what the solidification direction is based on texture. So I can't do a forensic analysis like that. And we've got to do more modeling. We have done some modeling on it to try and figure out exactly what's going on with solidification and stresses, but we need to do some more. We've done some very simple isotropic type models.
We didn't get the genetic texture. The genetic texture.
I don't know the word you're saying before texture.
We didn't get dendrites. Dendrites, they are.
Oh, so dendrites is the question. Are we seeing dendrites? So I didn't notice looking at things. I mean, we weren't looking specifically for dendritic structure, but it was more of a directionally solidified type of a structure, but without seeing the branches, it's more of just a kind of a uniform growth, at least in the center. So I didn't look specifically, but we didn't notice dendrites, no.
It depends upon constitutional underpinning of
Right, right. And it's being done relatively quickly, so it's, it doesn't cool down a lot, but it solidifies every time, obviously, so. Additive is interesting. I don't know if you guys are working on additive manufacturing yet, additive metals, but it gives a whole new set of problems that we run into that give us a lot of pain. But it's fun to look at too, so. Okay, so let's go ahead and break like we talked about a few minutes ago, and hopefully take 10 minutes, something. Okay? And if you come up with more questions during the break, let me know and we'll make sure and address those. Because right now we're just playing, right? We're just playing with the code and seeing what it can do. All right, 10-minute break. Which I'm assuming is going to be the same length as our 5-minute breaks that go 15, 20 minutes. So you made it back. Good. Was it his materials class or his materials for the ME? Oh, it was a metal forming one. Okay. So that was to the materials students. Yeah. Kind of Dieter, kind of like our 413 is actually what it is, but I think he does it much less mathematically than we do. We actually introduce tensors in our class.
But it was mostly mechanics.
Yeah. ask questions if you're getting some internet or else.
Yeah.
We've had a really struggle getting internet around here for, the students are giving us their passwords, so we're logging in on the regular network,
Right.
but it's really on and off, or keep it off, keep it on the others. But the guest house works pretty consistently, just really slow.
Right.
Just really slow.
That's true. Some tea. Did you go to the Nalanda building for that lecture?
Yeah. Already. Yes, are we ready? Okay, we can start. Okay, I'm live. Good. Okay, we're back. So I wasn't planning to show anything on some of this, but let's take a look. Since we were talking about texture gradients and orientation coherence, let's just take a quick look at this. All right. Interesting. Okay, so texture gradients or orientation coherence. We have to figure out, our function for texture, our ODF, we call it, orientation distribution function. We just say it's an f of g. And so if we include x dependence, then we can use this Dale operator that you became very familiar with from some of the conversations earlier, and figure out the gradients in that distribution. Now, it's not a single component. We have an entire function that we're taking in gradient of. And so it's to be represented, you have to represent it over ODF space. So one of the ways to do this is to look at, this is Rodriguez space now, right? Remember Rodriguez space. So this is just showing on the outside of the Rodriguez space where the orientations would be, and this is for an FCC rolling texture. So this is FCC rolling. And then it says if you move from a point that hasn't been deformed yet to a point that's starting to be deformed, this is how your rotations are evolving. So this is one of the ways it shows how the gradient evolves. All right, so you just have these arrows that are showing how the orientation's evolving. You can see the arrows are pointing into where we have the final texture positions, right? And actually what we should do is we should do that through the entire three-dimensional ODF space. So if you look at the entire space, you get a orientation flow like this that will show you an orientation coherence. It will tell you if your texture is periodic, or it will tell you if you have some specific types of gradients in the structure. So let me get out of that. And I thought, last thing I was going to show you, just a very simple second look at wire arc additive. And this is one of my PhD students. This is the one I've talked to you a few of you about what some of my different students are doing. This is the one that has a weld certification company that she runs. So this is her in her shop. And what she's doing in her wire arc additive is just actually joining two big plates. We have about 2.5 centimeters between the top of these plate, and it's about a 3 centimeter wide, thick plate. And that's just showing a map from the fusion zone out to the heat affected zone. And you can see, the difference in grain size, obviously. But this one turns out to be quite a boring texture because the base metal, you have a weak gamma fiber that you would expect to get in a thick steel plate, right? So thick gamma fiber. If you go to the heat affected zone, it actually kind of switches from being a fiber to where you have individual components, but you still get that 1-1-1. But now it's more of a 1-1-1 kind of 2-1-1 type texture. And then when you go into the weld nugget itself, you still retain that base metal texture. So it all kind of looks like a gamma fiber like you would expect from a base metal. And that happens sometimes, and it depends specifically on how the welding's done. And in this case, it was very thick passes. So we're going 3 centimeters of thickness that she's doing the wire arc additive on, and doing it in only 3 passes. So she's filling up a centimeter in each pass. So pretty significant filling. Anyway, kind of boring texture, but a cool project. Yes.
Maybe it's a fundamental question. From the ODF maps that you just showed,
Uh-huh.
you're showing 001,
Is this the map? Oh, coming up. So show us the plot of the slides again, please.
You're showing 001, 011, and 111. 4
Right.
figures.
Mm-hmm.
However, it's actually concept thing. That means that my 11 fiber showing the 114 figure,
Yeah.
the weight wire, still that one is represented in the 001 and the 0114 figure. So it doesn't matter which four figure I'm representing, my fiber is seen in the 3 4 figures.
So the 3 pole figures are showing the exact same distribution. That's what you mean, right?
Yes,
There-
it's showing my fiber. The fiber in the 111 is in the middle, center.
Right.
And my 001 is actually doing that ring
Right.
around the center.
Right. So that's 35 degrees away, whatever. Mm-hmm.
So it's the same thing.
Yes.
Doesn't
Yes.
matter how it shows, as long as it's a fiber, it will show either in the center
Right.
or like show next.
Right. So the question I think is, it doesn't matter which one of these pole figures we show, it's showing the same type of information. But remember, when you show pole figures, it's a 2-dimensional distribution. So you're not getting the complete information. So if you're showing 3 different views, then you have more of the complete information.
So in
Right, I
that-
think of it as like mechanical drawing where you're showing a top view, a side view, and an end view.
Okay. So, but still, that means it's better to represent in terms of ODF, like 3-dimensional, like 3-dimensional coordinates.
Right, so the follow-up comment, which is correct, is that it's better to represent it as in ODF space, either in Rodriguez space or Euler space of some type. And that's the more complete representation. Yeah. We show pole figures a lot because they're historically familiar to people, so they're a lot more familiar than Euler space plots, and certainly a lot more familiar than Rodriguez space plots. Mhm. Anybody else before we move on? Okay. So there were questions earlier in the week about some indexing. So I wanted to come into this demonstration program. And what we've done with this demonstration program is you can click and it brings up an image that's stored. And it doesn't know, there's a data set of images that are FCC or BCC or HCP. So there's titanium, and there's steel, and there's nickel. So that's the 3 phases that are in. And so anytime I click it and tell it to capture a pattern, it captures it, and then it does the indexing. So one of the things we were talking about is the difference between ferrite and austenite. Okay? So here is a ferrite image, and you can see if you look at the votes now on this one, in the Huff parameters, we've told it to find, let's check in Huff, we've told it to find 10 bands. Now if you do 10 choose 3 and figure out the maximum number of bands or maximum number of solutions that are possible, there'd be 120 possible solutions. So you can see on the BCC phase, there's 118 solutions that were found for that. If you look at the FCC, there's only 10. Even though 2 of those bands are shared between FCC and BCC. So if you look at the FCC phase, you have 111 and 311, but you also have 200 and 220. If you look at the BCC, again you have, this says 110, but that's the same as 220, remember, as far as EBSD is concerned. You have 200, you have 220 or 110, and then you have 211 and 310. So these 2 bands are different for BCC, The two bands on top are the same that you would get that are in both FCC and BCC. So there's a pattern, for example, that you would get from FCC, and you can see how it changes for the same orientation in BCC. So it changes pretty significantly, right? So generally, if you're finding bands, usually we tell it in cubics to find about 7 bands. Typically, we're going to get about 35 solutions all the time for that, right? If we have good patterns. The reason we jump the number of bands up is to look for lower symmetries, such as the hexagonal ones that are in this description. And so the titanium here has a lot more bands that are possible. And so almost always, if it, so this is an FCC pattern. So it has 120 votes, but it matches almost 20 votes and 19 votes it matches for the titanium structure, which is matching more than the BCC structure, even though 2 of the bands are exactly the same in BCC. And the reason for that is the titanium patterns, if we come here to the simulation page again, the titanium patterns are so much more involved. There's a lot more bands that are within the pattern than what you see in cubics typically. So the poles are a lot busier, right? This one has about 8 bands around it that are going through that zone axis. And with FCC, you wouldn't find, more than about 4 through any specific zone axis. Okay, so typically you're going to use about 7 bands for cubics. If you get lower symmetry, I would use 10 to 12 bands. Now there was another question. Let's pull up a titanium pattern. There was another question about bands that, maybe if you don't quite know what bands should be in there and you kind of know the solution, but you don't know the solution, and so you're trying to figure out what reflectors you should use. You can come to this page in your indexing. Here's all the planes that are being used, right? Here's all the reflector planes. So the red ones are the basal planes. So that's that plane through here. And then the yellow one is going to be a 10 bar 1 type of a plane, a prismatic type of a plane, which is these 2 yellow ones being shown. And here's another one there, right? So, in this one, we're finding the bands pretty good. There's a band coming through right here that is not being indexed, right? That one's not being shown. And maybe it's not found in the HUF, right? There it is in the HUF. We didn't find it. But maybe it would be, right? It's just maybe one that's not in our data set. So I can click on my shift button and say, okay, that one's going to come from about here to somewhere like this. And that says, okay, that is a, have to put this on to read it, 2 bar 1 4. Okay. And so I'll say, yeah, let's go ahead and add that one. So now it adds it in. So now it's part of my solution, right? It added it here. So I can come in and I can build up the structure for an unknown phase if you have a difficult phase that you're just trying to figure out what bands are being found and how you're indexing them. You can add those, or you can say, well, maybe this pink one is such a weak one that we're not going to use that. So you can take that out of the indexing. And ultimately, you have to come to the phase that you're using and modify that phase according to what's being used and what's not being used. Okay? So you can come in here, click your right mouse button and add or delete different bands. So this is the one we just added. This is the one we just deleted. So it's done that for us. I don't want to do that, and I think it would undo them anyway, but let's go back to how it was. And then we just go through and index. Okay, any questions that brings up from that? That was from some question. I think it was an online question somebody was asking. But I said when we get to this and start playing with it, I would show some of these things. Any questions? That's mostly if you're just starting to do some kind of unknown phase, right? A lot of oxides or borides or carbides or nitrides or something like this will give you some really complex phases. And there'll be a lot of different options for, as far as the chemistry of what they should be. So it's good to go in and say, okay, this is exactly what I want to use. Yes.
Generally, when we do an EDS things for FCC, BCC, or HCP, what about all the cases specified to double monoclinic? Like, is it possible to actually acquire like Ichiban from that?
Yep. So the question is, in what I've shown and what you do here, typically you're doing FCC, BCC, or titanium or magnesium, some HCP structure. So is it possible to do monoclinic or triclinic or trigonal or all these other systems? Absolutely, it's possible, and we do it quite often. If you look at the possible structures, we go to the data set. So let's just say, let's load a phase. Here are the phases that are possible. Well, these are just the phases that have been done. And this was the 7, so this is one data collect 7. So here's all the different ones that are available. So let's grab something we think might be kind of a funky structure. Uranium, titanium oxide, brennerite, something. So we'll open that one. So this structure is a monoclinic. Here's the lattice parameters. Here's what the patterns will look like for different orientations, right? So there's a database of several hundred that have been done. And always when we come up with new stuff, you know, we're looking at a new material, we're looking at some rock we've picked up out of the street, something, you know, that's giving us diffraction, then we go in and we create a new data file for that. Okay. So yes, the answer is yes, you can do a whole bunch of different types of structures.
So that's in terms of UGC, okay, and in terms of bulk texture analysis, because eventually whenever we get the code figures, we have to index them. I mean, we need to compare with something, and there is actually very few literature which shows that we expect from a monoclinic phase, for example.
Yeah, so he said, oh, okay, so now we can index them. So you're convinced that we can index them now with eBSD, but now texture analysis is a problem, right? So, you know, we know what FCC rolling should be in HCP and BCC, but what do we know about rocks? So if you go to the geology department, they know a lot about rocks. And they actually take this, they take specimens from different mountain ranges, and they'll do a texture. The geologists call it fabric. We call it crystallographic texture. They call it fabric. Although the geologists were the ones that first came up with the word texture in the 1920s. But they've switched, they use fabric. So they'll tell you what the fabric is, and they'll say, we know that mountain range developed at a given temperature, and it was, you know, a shearing thrust to develop that mountain range based on what the texture is. So just like we do with metal deformation and forensics and say this is how it formed, the geologists will go in and do the same type of analysis on the fabric or the texture of geologic specimens, and they know quite a lot about it. So there's a lot known about non-cubic and non-hexagonal structures. So I don't know anything. I don't know much about it. I sit in meetings and I say, oh, that's pretty neat. Yeah. You're looking at forsterite, that's cool. You know. And I've done a lot of measurements for people like that, and they'll send me stuff and say, put this rock in your SEM. I say, okay, I'll do it. And measure something and send it. And then they can do the analysis and comparison. But I've never learned that stuff. But it's, yeah, if you study, look up geology or geologic formations and fabrics, and you'll see a lot of this stuff. Okay. Okay, other questions?
Sir, just following this question in more detail, let's suppose I have a copper foil around 25 micron thickness, then I have electrodeposited tin over that, which is around 10 micrometer thickness, and I think electrodepositing that tin, and after that it is applicable for the battery anode. So after that I have discharged that, and at a particular potential, let's suppose over a parent phase, which is when lithium is getting inserted in tin. So over Li7SN3, which is monoclinic mesoscale, Li7SN2 forms at a particular potential through nucleation and growth process. So can I do the texture analysis and do all this study?
Yeah. Yeah, so this is a very good question, and I'm not going to repeat the question because I don't remember all the materials. But he talked about all the different layers that would be formed on an anode, right? You're looking at the anode structure for lithium-ion battery. So let's look at a new data set here. And let's see if I can find something that will give you some warm fuzzies, if you know that term. So we're looking at samples and chi-scan. So I'm going to take I'm looking for a demonstration data set. And there's one with a chi-scan, right here, interconnect for chi-scan. I don't know if that's the right one, but let's see what this structure gives us. So there's a data set that at least used to be demonstration data set that has about 6 different materials in a layered structure. And it's not this one, shot page. This is some kind of geologic specimen. Silicide detail. Okay, so I can't find the one I'm looking for. Let's see what one of these looks like. All right, so here is a data set that has 4 different phases in it. So if I do a phase map, yeah, that's kind of a boring phase map. I thought it would be a little more interesting. But sometimes what I was looking for had a bunch of layers, like you're describing, right? So this is 4 different phases. And you can certainly see the red and green phases, the rhodochondrite or whatever, barium sulfite. There might be a little quartz in there, and then there's some pyrite in there. So this is a geologic specimen. A bunch of different materials, a bunch of different structures. Some are small grain, some are large grain. So this is a pretty complex structure. So you can go in and you can determine that, right? You can measure that layer sequence, assuming you have enough spatial resolution, assuming your grains are large enough that you can actually do EBSD. Or you can do TKD maybe if you can't see them. That's transmission Kikuchi diffraction. That you do also in the SEM that your techs know how to do well here. And then you would look at each individual phase and structure and look at the textures. And so, you know, let's look at this barium sulfite phase, which is this green phase here, and we can pull figures. I don't even know what the crystal structure is. Let's see if it tells me here. Yeah, so it's not telling me, but the information that it has here is saying that it was done with these 4 phases, but it also was checking at the same time it was doing EBSD, it was doing EDS. And so it had EDS counts on all these different types of phases of elements. And that's a lot of times we'll use that information to distinguish between phases as well. So if you have copper and nickel together, they're all FCC and they'll just index as FCC if you don't have the chemical information in addition. Right? So you need that sometimes to say that's a copper layer, that's an aluminum layer, that's a nickel layer, and that's a stainless steel layer or something that all look FCC. So sometimes you have to bring EDS in as well, but the data you can get, and you can do texture analysis on all the individual phases. Okay. Okay, anybody else? Any other questions?
Is it possible
Yes.
to do EDS and EDSD simultaneously?
Yes. Yes, it's called chi-scan, CHI, chi-scan. And I don't know that you have, I'm looking at people who've done EBSD. Has anybody tried to do EDS at the same time? No? So maybe possible, maybe not. In OIM Data Collection 7, I think you guys are using Teams though, right? You're using an Apex software or something, or Teams at least. So I think it's possible. I mean, maybe it's a license thing. Maybe either you can or you can't based on what your license says. But my guess is it might be possible and you just haven't tried it yet. That's my guess. Another question?
How to show the orientation relationship between 2 different phases?
All right, so the question is how can you show an orientation relationship between two different phases? So that is also a great question. So let's look at this barium sulfate, which looks like it's a trigonal structure. I think that's trigonal. And let me see, quartz was not very much. So for the first 2, so we had I can't say, I don't even know what they were. We'll just call that rho and we'll call that barium something. Okay, so this is a showing 010, which is different than 100, which is different than 001, but it's in this square. So this barium sulfate is going to be a orthorhombic structure, right? So all the angles are 90 degrees. A does not equal B does not equal C. And then this is a trigonal structure. We have a 3-fold axis and similar to hexagonal, but it doesn't have the hexagonal symmetry. So it's just 3-fold instead of 6-fold. Okay. So these 2 structures. So we're trying to find an orientation relationship between them. We know that if we look at the phase map, these long blocky looking things are going to be the barium sulfate. And so let's go back to this map and say, okay, is there some kind of relationship between this grain and this grain? Okay. Now, if you click on the lattice, you can just kind of get a view of what things look like, right? So there's the trigonal structure, there's the orthorhombic structure. It's hard to tell if the axes line up in any way, right? Just looking, I can't come up with anything specific on that for me. So we can come in here and we can do an interactive analysis. Now let's click on the boundaries again. We'll click on this, whoops, click on that point, click on this point. I've got to tell it to record, sorry about that. So this button is important, that makes it record what you're clicking on. So I click there, come over and click here. And now it's telling me that there's a 85.69 degree rotation about an 11.53 axis in whichever one of these I clicked on first, which is going to be the orthorhombic structure. That's this blocky one. And there's the axis is 9091 in the trigonal case. And then it tells me the 2 planes that are lining up, assuming that the grain boundary goes straight down through the material. right? And so I've clicked across. So the bisecting plane is 11012 in the first grain I clicked on, the orthorhombic plane, and 54111 in the trigonal plane. So those two planes are coincident with each other, we know that, right? So that's kind of what we can get from this, that they share some rotation axis that's the 1153, and so these two axes line up with each other, these two planes line up with each other. So is there some relationship from that? You know, we'd have to do a bunch of those to determine if there was some kind of specific orientation relationship. Right, so I can click on this one and come over to this one and say, are those similar? You know, does it look like some kind of similar information I'm getting? Okay, so it doesn't directly give you an orientation relationship, but you can pull out a lot of information that will help you, you know, help you as a scientist to figure out what that relationship might be. Okay, that's a good question. Anybody else?
You can also give the line. It's a relationship means the plane as well as the line.
So the line that it gives is the axis that's shared between the two frames. So if you look at the misorientation, you know, the second one I clicked is 13-degree rotation, about a 1924 or a 113, 14, 12, right? So that means those two directions line up with each other, okay? Those two directions line up with each other. And it just happens to be the directions that line up with each other to cause that rotation. And then these are the planes that are lining up with each other, assuming that it had some kind of specific plane. Let's look at this one across here. So it's a 91-degree rotation now. I clicked it backwards from what I did to the others, so I should start in the orthorhombic and go to the other one. So you get information, but you don't get directly. It's not going to just jump out and say, here's a Nishiyama-Wasserman orientation relationship or something. Right?
Can you show it in pole figure?
You want to show a pole figure?
Yeah, can you show the relationship between two phases in pole figure? Is it possible?
All right, so that's another good question, and I'm going to do this and then I'm going to stop. This is actually a great place to look at. So we have the barium sulfate pole figure. Let's make these dots big. Okay, now those dots are big. And then we're going to do a pole figure in this roto, whatever it is. And you choose which pole figures you want to look at, right? So you can choose a whole bunch of different pole figures. Wow, too big. Yeah, let's just make these a little smaller here. But I still want to make them big so I can see them good. Okay, now let's come to here. Let's delete the ones we don't want. Okay, and I'm going to tell it to show highlighting. I'm going to tell it to show highlighting. And so, what did I do? It just has a lot of data points on that one. Yeah, let's just leave it. I won't tinker with that too much. But there should be a way I can go in here and just erase, oh, show points, good. So I can erase that and just not show the points, good, okay. Okay, so now I'm going to do this. I'm gonna click across the boundary. We'll do it in here. And we're going to click on one, click on the other one. This one is not showing me. It should be showing me a point in both that I've clicked on, right? So let's just look at individual points, see if it's going to click. Show highlighting, it should be showing highlighting. So anytime I click on a point, it should be coloring it up in. Oh yeah, it's just going on top of each other in this one, right? So am I clicking on the wrong one? I thought this was a rotocrossite. Yeah, somehow it's not showing me in this phase. Maybe if I show a different pole figure. And this one that I just clicked in, by the way, it says here's my pole. It's a 101 or a 101 bar 1 in Miller Brave. And the direction is completely different than that, right? Because it's not cubic. So then there's 2, and when I click, they should come up, but somehow it's not coming up. So anyway, so theoretically, they would come up in that data set, and you could see them directly in the pole figure just by clicking. And alternatively, like I showed you before, you could click on the pole figure, and it should color everything that it's oriented like that in the maps. All right, so I'm going to stop here. I'm going to be around to still the rest of the day and tomorrow, and I don't leave until Sunday, and so if you want to chat about things, I'm happy to chat about stuff. So, but I'm going to turn the time over to Shomik here to finish up. Okay? Thanks.
Okay, thank you. Okay, hello everyone to today's lecture. So far we have seen a couple of different methods, molecular dynamics and density functional theory, with a background theory in statistical mechanics and how they can model various thermophysical properties and look at phenomena such as electron transfer, deposition of molecules on surfaces, and so on and so forth. One of the challenges with any of these approaches is how limited they are in terms of length scales and time scales that you can access with these methods. While they are quite accurate, obviously if you use a quantum mechanical level theory, then it's the most accurate. Then you might consider molecular dynamics at the next level, but they are limited in terms of the length and time scales. So today we will talk at a less frequently used approach, but can be pretty handy, which is called kinetic Monte Carlo approach. So the methods we have talked about so far were all deterministic, meaning you are basically solving a governing equation, and from that solution you are using principles of statistical mechanics or quantum mechanics to look at various phenomena or properties. Here on the other hand, this is very distinct from these methods. This one, kinetic Monte Carlo, is a stochastic method. So it models what we call a Markovian chain process, if you have heard of that. So I'll introduce that in a moment. But here's the idea. So let's look at this kind of animation here. So you have a crystalline structure surrounded by solvent and crystallites. So let's say we are talking about solution crystallization, and we are interested in deposition of these molecules to grow the crystal further, which we have looked at a little bit when we looked at, though it was not homogeneous, it was kind of heterogeneous. We looked at deposition of PCBM on top of perovskite surface. If you are doing this at the atomistic scale, you can see individual deposition or dissolution processes that can happen at the crystal surface at various sites. There can be step sites, there can be planar sites, there can be corner sites, and you will see individual deposition events happening. Okay? But again, I mean, if you model this, you are limited to let's say hundreds of nanoseconds, where it's very difficult to observe a complete growth of a layer of crystallite on top of this surface, let alone multiple layers of crystal growth. So one approach that has, in the recent times, I would say about 10 to 15 years time frame, looked at modeling such problems is the kinetic Monte Carlo. Like I mentioned, what kinetic Monte Carlo does is it models based on a Markovian walk, which is basically time evolution of a system from a state A to a state B with a certain probability of different events that can happen. So the question is, can we use kinetic Monte Carlo to model this system? And then kinetic Monte Carlo relies on some of these transitions in states happening while these deposition processes, for example, are going on. How do we measure the rates for these processes? One approach that can be used potentially is either measure those rates of individual atomistic level processes, kind of challenging, or you can run a high resolution modeling such as at the molecular dynamics level, and capture those rates of individual events and then propagate it through a stochastic framework. So here is the master equation that I mentioned. This is very generic. It's not only valid for physical systems, they are used in other disciplines as well. It's basically a system is at a certain state A which occurs with a certain probability at a given time, and then it tracks how that system goes from the state A to a state B through various events that can occur, right? So these functions W A to B is basically kind of a probability per unit time, you can think of it that way, for the system to transition from the state A to state B, with this probability of the system staying at state A or staying at state B. But it's an incredibly challenging equation to solve analytically, simply because you have to kind of account for all the tremendous large number of events that can happen as the system does its Markovian walk. Okay? So, what kinetic Monte Carlo does is it numerically solves this master equation by generating a trajectory or a collection of trajectories, stochastically speaking, where in each of these cases the system kind of evolves with time from state A to state B in a non-linear manner with time. In molecular dynamics, because it is a deterministic process, you have a certain time step in your velocity Verlet algorithm to kind of integrate the Newton's laws of motion to take the system from one step to the other. In this case though, it is based on random number generation, as we will see, and therefore the time that you kind of sample does not have to be linear. So yeah.
So in this case, you can see like one forward reaction and one backward, just kind of that.
Right.
Over both the summation are over B state, so will be not one B and one A.
Because you are thinking of it as if you were at the B state, what are the chances of it getting from A to B versus you are at the B state, or getting from B to A. So that state itself in the master equation is based on the state you are trying to get to, which is the B state.
In one case we are thinking about the final state, and in one case we are thinking about
Right.
the state.
So what I have here is kind of an algorithm for kinetic Monte Carlo, which we will look at some examples of. At this point, let's just kind of have a general understanding. So the algorithm is based on identifying the various events that occur for this particular system and the rates at which it's happening. Like I mentioned, one way of measuring those rates is through molecular dynamics or another simulation methodology, and then define a function, which the function is adding up the rates for each of the individual events A to B that can occur, and find a cumulative function which includes all the different observed transitions. Once you have that function, you can stochastically generate a random number. So think of this function as a line as I have drawn here. So this is the entire spectrum of events, and each event, some have a larger transition rate, some have a smaller transition rate. So you've kind of generated a cumulative function. If you use a random number generator and multiply it with this total value of the transition, which kind of captures the length of this line, essentially what you are doing is coming up with a location for this random number generator, from which you can then pick, let's say this is event 1, 2, 3, 4, etc. Depending on what random number you have generated, you can pick this particular event and proceed with it, and therefore evolve the system from the initial state to the next state through this algorithm. We'll look at specific examples. So this schematic again shows you a situation where you have distinct steps in, let's say, a crystal growth process, where there are deposits happening on top of a surface at various sites. You can define these sites based on the number of the coordination number. For example, there can be a site which doesn't have a surrounding atom or molecule, or there can be a site with a coordination, or there can be a site at various levels of coordination, and then you can have individual atoms or molecules that are depositing on top of the surface at various sites. So while you can again look at this based on at the atomistic level, it's kind of restricted in the time scale that you can model. But if you measure the rates of each of these processes and define a cumulative function for the transition rates, then this schematic is kind of showing you in a stochastic manner how this is just an example of how this crystal can grow or dissolve depending on the surrounding medium. Another example of how this method has been used is in a very different application, which is a growth of a nanoparticle. In this example, the one I am showing you is soot precursor. When you have combustion processes, there is soot that is generated, and one of the soot precursors are these polycyclic aromatic hydrocarbons. This one is pyrene, there is coronene, and the chemistry of it is measured through various chromatography and other measurements. You might know what the rates for the surface reactions for this particle is. You can use those, or you can use those rates from density functional theory calculations to kind of evolve the structure of these soot precursors, starting from very basic unit to much larger structures. So, there are very interesting wide range of applications of the kinetic Monte Carlo in principle. I will kind of present a couple of specific examples from my own work in the past.
Can I ask you a question?
Yeah, sure.
So the probabilities are associated, a Hamiltonian associated with those that gives you the probability A and B over a time somehow. That's how the time step comes in.
That's a great question. The time step comes in through the transition rates. So you don't define the total energy or Hamiltonian because this is not really a Hamiltonian dynamics involved in this process. The time is coming in from the total rates of the processes that you have. I will show you the specific model for time in a couple of minutes. I mean, the total rates are normalized from which you can estimate depending on what event has been picked. Time is kind of calculated based on the event that was picked. It's post-processed based on the array of events that you have. You can think of the total transition rate as kind of a Hamiltonian if you want to. I mean, you define a priority what your event space is,
Because the probabilities have to be defined, right?
Yeah, the probabilities have to be defined. The probabilities in this kinetic Monte Carlo are defined in terms of those rates. So it's not normalized. There's a total, each have a certain frequency of occurring each of these transitions from that perspective. Okay, so one example that I will present is kind of continues with the discussion from the discussion we had on Wednesday of these molecular deposition process happening on a perovskite surface. What we saw from that calculation at the atomistic level is we were only able to look at a handful of atoms or molecules depositing on the surface. Can we propagate it to a much larger length scale based on the kinetic Monte Carlo approach? Let's say going from a surface that is at best 10 by 10 nanometer to 100 by 100 nanometer, or it essentially can be at the micrometer scale as well. And modeling processes over a time scale of 60 nanoseconds, in that case fully atomistic simulations to microseconds. So, let us look at that as an example first. There are two flavors of kinetic Monte Carlo. One is on lattice, the other is off lattice, and I will show you one example of each. On lattice means, as the name suggests, you have some specific locations where those events are happening. So, it is not free to occur. For example, this is an on lattice example, the crystal growth, where there are some specific sites where those events can occur, versus this one here is an off lattice, because you are not restricted to a certain site. It can kind of grow in many different degrees of freedom and have various fractal dimensions. Okay. So, the first step in kind of scaling up the example that I presented with kinetic Monte Carlo for the molecular deposition or layer deposition is to capture, to come up with a list of events that can happen at the surface. In this case, the events are deposition of those molecules, the PCBMs at specific sites. And the good news is the atomistic simulations, if you remember, gave us pretty good resolution. I can show you kind of very quickly my slide from Wednesday. So, we looked at, remember, various different configurations how the deposition can happen, and we also looked at the attachments that can happen between the molecule and specific sites, in that case lead atom of the perovskite surface, right. So, we have a good idea of the specific attachments and sites where these depositions can happen, and now we want to propagate it through this stochastic framework. The questions are, can we, if this is successful, can we capture things such as the deposition rate, the distribution of the clusters that form as these particles deposit on the surface, look at surface coverage and morphology. The reason this is important from a photovoltaic perspective is, essentially the electron transport layer, the more uniform it is, the better it is for device performance, because the electron transfer pathways are more well defined. Okay? So, you want to have a defect free deposition. So, this came from our molecular dynamics simulation. Remember the different surfaces on which deposition process can happen and the nature of attachments. Okay. So, going back, how do we think of this problem from the master equation? So, the master equation is very general. What we do is, instead of thinking of the W function, we think of these events in terms of, like I mentioned, the transition rates k. Transition rates are basically rates how frequently each of different events that we define occur, okay, that we can then propagate from one step to the other. And then if you do that, you can relate it to the total transition rate. So, it is basically you have to kind of come up with a series of events 1, 2, 3, 4, and then you have to kind of measure or model or estimate the transition rates for each of those events and come up with a cumulative function for the transition rate. Okay. The process is, once you have the cumulative function, you draw a random number. In this example, we are calling it, let us say, u1 between 0 to 1, and then it is not normalized. So, you kind of multiply it with the total transition rate, which makes it fall between a range of 2 specific events. Okay. It makes it fall between 2 specific events, e minus 1 and e, and once you have identified what event, what range, where exactly it falls in the array of events, you can, it corresponds to a very specific event that is happening, and then you can evolve the process. And to Dave's point, you can think of, you can now estimate or kind of calculate back an essentially a time scale that is associated with this event, because it is an exponential function. This is how you can kind of calculate the time scale as the natural log of the of the random number of the over the total the cumulative function, basically, of all the transition rates. So, what you are doing basically through this process is, let us say this is a very complex energy landscape, where you are located here in a process, kind of a in this case it looks like a global equilibrium, but it could be a local equilibrium. So, you are oscillating here and capturing the configurations, the energy configurations associated with this landscape. It is very difficult for molecular dynamics to escape this energy barrier to sample kind of very different configurations, such as in this case B. The kinetic Monte Carlo does this jump to kind of go from A to B in a discrete step, and the frequency of that process will depend on the transitions rate for that specific process or event. So, now how do we apply this methodology for growing this layer? Well, we have to know a few things. That is why it is important to either characterize or run calculations to understand the attachment mechanism. So, in this case, we have seen that these particles deposit with the the Fullerene moiety pointing upwards, and its esteric moiety here, this chain, specifically the carbonyl oxygen forming some sort of a coordination or association with the lead atoms on the perovskite surface, right. And that is evident from and we see at what distance this happens. So, what you see here, I think I presented this on Wednesday as well, is a location from the surface where the carbonyl oxygen is with respect to the lead. So, you kind of know the location, and then you also know the distance between, you know the structure of the surface of this perovskite and where the lead atoms are located, and how the structure tells you the distance between neighboring lead atoms in horizontal, vertical, or if you want to call it in the x, y and the diagonal direction. So, you can have discrete deposition events of these molecules at each of these locations. It is like a grid. Okay. So, how do we kind of catalog this set of events? How do you define in what location each of these deposition is happening? So, here is a schematic to kind of illustrate that. So, you have this grid, which is not really a square grid. You see these are rectangles, because that is what we have on the surface for the arrangement of the lead atoms. So, you can define the location of each of those points based on how many neighboring atoms or how many neighboring PCBM molecules are present with respect to a certain location that is going to have that deposition process happen. For example, this location 1, it has some neighbors, as you can see, in terms of if these blue spheres are already deposited Fullerene atoms or PCBM molecules rather. So, we came up with a kind of a scheme or classification to identify each of these locations. What we associated a weight of, this can be done in many different ways. In this scheme, we associated a weight of, we call this x direction, the number of neighbors in the x direction, we associated weightage of 1, y direction 2, and z direction 3. Okay. So, depending on the site, for example, if it's the site 1, we have 2 neighbors along the y direction, we have 1 neighbor along the z direction, and 3 diagonal sites that are already occupied. So, based on this, we can come up with a function that says this n, that says what sort of deposition site it is where the PCBM molecule will deposit. Okay. So, from the molecular dynamics simulation, we can estimate the transition rates or deposition rate at each of these sites. We can directly measure and have those rates tabulated. But in the kinetic Monte Carlo, we just pick one of those events and we kind of make it happen stochastically to kind of fill up these sites and deposit those molecules. We came up with a definition of these transition rates based on the total number of events that we have and the specific event that's occurring, the time scale, and the total number of time intervals that we sample, and we can normalize it with the surface area as well. So, this is just to normalize the surface. So, if we kind of proceed with this framework and let these discrete deposition events happen based on the random number generator with the kinetic Monte Carlo model, we can characterize many different things. We are basically filling up the surface with this deposition, and as that happens, we can look at the rate at which these deposition events are happening at various physical conditions. So, how do we model those physical conditions? Those physical conditions will depend on how we kind of estimated or calculated those rates. For example, we can run these molecules, let's say PCBMs, in at various concentrations in the solvent. In our case, the solvent we looked at was chlorobenzene. We can have a concentration of 0.8 molar or 0.24 molar, and we can vary these conditions. We can look at different temperatures. We can look at very different solvents. So, basically, we can vary the processing condition under which these deposition processes are happening. The reason we chose somewhat higher concentration is because the way these films are deposited is through, once you deposit these, there is evaporation of the solvent and you can reach pretty high concentration. So, we are interested in looking at 0.18 and 0.24 molar concentration of these particles. When you plot the rate, the number of deposits with time, it's nonlinear. It looks like a kind of a smooth line, but one of the advantages of this is because this is a stochastic process and it's quite fast. For each of those surfaces, for each physical condition, you can run hundreds of kinetic Monte Carlo calculations, and every time, because it depends on the random number drawn, you will have slightly different trajectory for this deposition process. It's not deterministic, so there will be some variation. So, if I zoom in, you can see that there is some difference in how these deposition process is happening for every time I kind of run this code. It's an in-house code. And so, basically you have the surface coverage happening on the number of deposited PCBMs happening in this nonlinear fashion, from which you can calculate a few different things. You can determine the surface coverage at each point of time during this process. So, in our case, we kind of simulated the two systems up to about 1 microsecond, the 0.18 molar concentration to about 1.03 microsecond, while the higher concentrated system to about 1.13 microseconds. And we were able to estimate the kind of a rate at which the surface coverage is happening. Let's say in this case, it was slightly higher for the lower concentration than for the higher concentration. So, we got about 5.6 nanometer square per nanosecond deposition rate. There are obviously the underlying physics of why the rate is higher for the lower concentration versus the higher concentration depends on the specifics of the molecular interactions. So, with 0.24 molar concentration, these PCBM molecules tend to cluster because it's quite a bit higher concentration. So, now you have, instead of individual PCBMs depositing on the surface, you have a cluster of 2 or 3 PCBM. So, the diffusion is kind of proportional or related to the size of these clusters. So, as you go to bigger clusters in the solvated phase, the deposition process, it diffuses slower towards the surface, and the deposition process is slightly slower. So, from our molecular dynamics simulation, we observed the same trend, that with the higher concentration, the deposition rates are for each of these events are somewhat slower. So, when we look at these two concentration lines that are kind of designated as C1 and C2 in here, C1 being the green line, or rather the red line, which is 0.18 molar, and C2 being the higher concentration, do we see different modes of how these depositions are happening? So, we could identify 4 distinct regions for this. This is region 1 from the distinct slopes. There is a region 2, there is a region 3, and then here is region 4. So, why are we seeing a gradual change in the rate of this deposition process, and are the characteristics very different? So, let us investigate that a little further. We can determine that if we take a look at the surface while the deposition is being modeled with the kinetic Monte Carlo, and look at not just the number of PCBMs that have been deposited, but what is the morphology. I mean, is there a certain distribution of the number of nearest neighbors? Can we come up with clusters of 2, 3, 4 or bigger clusters of these molecules that are depositing, or are they depositing primarily at isolated spots? Remember, these rates are very different because we measured these rates and they are not identical. So, can we analyze the surface distribution for these particles? That is something we were interested in. What we found is the first region at the beginning of the deposition process, let us say the first 200 or 250 nanoseconds, we have smaller clusters as expected on the surface, and it is kind of heterogeneous, though there is a little bit of a distinction between the two concentration. With the higher concentration, there are a few big clusters that are starting to form even at the initial phases. As we go to the second region, we have increasingly larger clusters, partly because of the kinetics, and there is not enough empty spots left in the surface for those deposits to happen. And finally, as we go to towards the end, there are even fewer spots for the deposition to happen, and we see kind of merging of the different clusters due to deposition of PCBM between two clusters. So, let us take a look at the surface. So, we could come up with an animation, let us say, of how the surface is getting kind of filled up with time and with surface coverage. You can kind of, this is a neat thing you can do from this simulation. Remember, these are at this point, these are coarse grained. Each of these dots are basically, you are looking at a single PCBM that is depositing. Okay. So, let us look at instead of looking at the entire evolution of the surface deposition process, let us look at few specific configurations at various surface coverages. So, let us first look at for instance, when the surfaces have an 8% coverage of these PCBM molecules that have deposited on them at 2 different concentrations. So, what we find, and we will analyze it through distributions, but even visually what we can see is in the first case for the lower concentration, most of these deposits are either at kind of isolated points. So, these dots do not have as many surrounded small clusters, or even if there are some, the number of nearest neighbors are maybe 2 or 3. So, there can be a cluster of small clusters, 2 or 3 PCBMs in there. While for the higher concentration, we observe there are some bigger clusters that are forming. We just came up this kind of this visual was also observed at a much smaller length scale from one of our molecular dynamics simulations. So, we kind of came up with this, but we wanted to also check if there are any experimental data that is available that can tell us about these clusters that are forming. And the imaging that we found in the literature was not exactly for PCBM depositing on perovskite surface, but there was something on gold. I do not remember the application. They were looking at PCBM depositing on a gold surface, and they saw some similar arrangement of these molecules depositing on a gold surface. So, this is kind of, even though we didn't have the exact same system where we imaged it, we saw some similar formations. As we grow the surface to a much larger surface coverage, to kind of, let's say, 60% surface coverage for these two concentrations, it becomes very difficult to distinguish how the structures look or how the distribution is visually. So, it is important at this point to come up with a distribution plot. You can take this and analyze the surface and find a distribution. By distribution, what do I mean? I mean cluster size distribution, essentially. I mean, for the two different concentrations, we can plot normalized as a percentage clusters of various sizes. In this case, the biggest clusters we had were about up to 18. So, if you sample more, perhaps you can see bigger clusters, but from our calculations at 56% surface coverage, these were the biggest clusters that were formed. So, what are the trends that we observe from this? Well, we can first look at the lower concentrated PCBM system that is depositing here, and we find that at the very beginning, when you have about an 8% surface coverage, which is the image that I showed you earlier, the surface map, the peak in the cluster size is, I believe, 1, and then you have quite a few dimers, if you want to call it, or trimers of PCBM that are depositing on the surface, but it's kind of a sharper distribution, with the biggest clusters that are observed is about 4 or 5. As it keeps depositing and reaches 48% or 56% surface coverage, obviously you have bigger clusters that are forming, but even at 56% for the lower concentration, the peak is about at 2, I believe, and the largest clusters we observe for that system is about 6 or 7. There are very few bigger clusters, but very few. This is distinct from the system with the higher concentration of PCBM that we modeled, where we saw a much wider distribution at larger surface coverage. This gray line shows you the distribution at 56% surface coverage. So, the bottom line is the morphology of these deposited film is very different depending on physical parameters, in this case the concentration in the stock solution. You could look at other effects, like I mentioned. You could look at totally different solvents. You can look at temperature and other processing parameters, which is basically the goal of extending this methodology, to look at all these processing conditions and see what is the morphology that is resulting from that. Any questions?
So, what kind of iterative potential do you use
For the molecular dynamics? For the molecular dynamics, it's the same. I presented that system on Wednesday. It was OPLS AA. It was an all atom potential model, but another option is to go for coarse graining. If you do coarse graining, which the next example I'll show you is a coarse grain potential based on the Martini force field. I don't know if you've heard of it. So, then you can model much larger systems even with the molecular dynamics, which can be pretty useful. In this case, it was at the all atom resolution, but even then I think the size of the system was at least 200,000 atoms. So, it was a pretty big system. We modeled it up to 60 nanoseconds, but the challenge is as you kind of have these are pretty slow diffusion processes in the solvated phase, because of particularly at higher concentration. So, the rates of these events become lower with deposition. The other challenge is, this is physically very meaningful. In MD simulation, what ensemble do you typically look at? NPT, or let's say NVT. I believe in this case we looked at NVT, the canonical, because we had two substrates and we didn't want kind of oscillations of the surface. So, we maintained a constant fixed volume which was carefully equilibrated. So, what is the challenge with that? If you do a NVT ensemble, a canonical ensemble is what you are modeling at the atomistic resolution. What is the challenge with this deposition process specifically? The challenge is you are depleting the number of molecules that are available to deposit on that surface as it happens, right. So, the driving force given by the concentration gradient, if you think of it from a continuum perspective, is getting lower and lower, right. On the other hand, the kinetic Monte Carlo essentially you are not limited by the number of PCBMs you have. So, it's in that sense, though it's not analytically formulated, but it's closer to a grand canonical ensemble, because if you're making these deposits, you have additional PCBMs out there to continue to do this process.
So why the random number is required?
Because you are trying to identify the transition. This is the event, let's say. There are many different events in the energy landscape. I showed you an example of the energy landscape here. So, this energy landscape is more complicated, right? It's not necessarily just those two events. So, you are here and you can land up in a certain other configuration, each of which come with a energy barrier and each of which come with a prefactor, frequencies of attempt, right? So, it's randomly choosing the next state that your system lands up at in the Markovian walk process. So, that is why it is a stochastic solver. If you are doing it with molecular dynamics, a deterministic process, you have to wait till your system climbs this energy barrier and reaches some other local or global minima in the energy landscape. And you do not even know the energy landscape. If you are interested in finding the energy landscape, which is something that I have not talked about, but in molecular dynamics it is very frequently done, you have methods to come up with the energy landscape, various sampling approaches such as method of collective variables. So, but it's not a very straightforward calculation, it's very time consuming. In this case, we know what those states are, we have observed, and we are able to carry it forward. Now, there is still a kind of limitation there are a couple of limitations in this method though. Number one, what if there are very rare events that you do not observe in the scale of your simulation in molecular dynamics, because it does not happen in 60 nanosecond, either because it is far away from where you are, the state you are at, the configuration, or because the barrier is so high, the system never explores that minima or local minima state. If that happens, then you are missing that in your catalog. So, when you are propagating this stochastically, remember your input is coming from either some experiment or some atomistic scale simulation, and it is limited to that input. So, that is one of the limitations of this method for sure.
So, this is also hybrid Monte Carlo MCMT thing.
You can call it that. I hesitate to do that, because I would call it that only if this is happening together, I mean simultaneously. This is not happening simultaneously. You have first a deterministic approach, and then you are plugging in something that you calculate from that to a stochastic solver. So, but yeah, essentially it is a hybrid method to investigate.
You are using the interatomic potential also, and for that you need to have the MD thing.
Yeah.
And this is solving the thing without considering the time evolution. So,
right.
I think it is hybrid MCMD thing. Means,
in that sense, yes. Yeah, go ahead.
So, you are using your in-house code for doing these sort of calculations.
Right.
So, how we can use our
Very good question, very relevant. So, there is a code that is open source. I think it's called SPARKS, SPARCS. It's made by the same developers as LAMPS. Most of you who are doing MD are probably using LAMPS from Sandia National Lab. That it's not as popular, but I have not used SPARCS, but SPARCS can do a few cool things, and I would suggest exploring it if you're interested in things such as, one of you mentioned you are interested in magnetic materials, right? So, there is a widely used model called Ising model, which looks at atomistic spin states, and it can just kind of stochastically, using a kinetic Monte Carlo or using a Monte Carlo model, look at upspin and downspin, and from which it can find magnetic dipole moments of atoms and propagate it. So, Ising model is in that code. There is kinetic Monte Carlo that can look at dislocation, crystal lattice dynamics. It can look at crystal lattice dynamics. There is a module there. I haven't used it personally, but it's a kinetic Monte Carlo solver, and it's somewhat well supported. It's not like LAMPS, quite, because it's not as popular, but that would be something that you can explore if you are interested in especially I would say an on lattice Monte Carlo. They do have also a module on off lattice, which is what I am going to present here, but it's tremendously more complicated and challenging to do off lattice.
So this icing models they come in package with VASP also?
I'm not sure. I'm sure VASP should have something like that, icing model. But I do know SPARC's has it. There are a few other, if you go to GitHub, there are a lot of Python scripts available, and icing model is a popular one. In fact, I had to write a code for icing model when I was taking a computational physics class. It's not very complicated. It will be about a couple of 100 lines of coding to come. I'm talking about C. With Python, it will be pretty crisp, small, short code for icing model, and it's pretty useful. Other capabilities that we have not yet added to this, and you might be thinking, is diffusion. When these particles deposit at a certain site, do they diffuse within the surface? For certain systems, that will certainly happen. With the PCBM, those attachments, and we have calculated energy barrier for it. I am not presenting here. We have a published paper which looks at the binding energy for these molecules with the perovskite. It's pretty high, so it doesn't really. And we have also looked at surface diffusion. Surface diffusion is pretty rare for this system, but certainly if you're looking at other sorts of deposition processes, that will be an event that you have to model, surface diffusion. And then there is one third aspect that I have not presented. I'm just checking if you have noticed that. You can certainly scale up, not along the surface, but what about multiple layers of deposition happening here, right? So the challenge with MD is it's very it requires a long simulation to observe stacking of these molecules one on top of each other, because how complex these organic molecules are. But if you're looking at a simpler atomistic system like some sort of a metal deposition, then you can certainly come up even from DFT or MD certainly energies for those processes to happen, right? One thing that I didn't mention, this is my approach in this case, but this transition rate, you can express it as sort of a prefactor times, right? You can, like in an Arrhenius form, you can measure only the energies for those events that you are interested in from density functional theory, and then you can guess this prefactor. So you can actually kind of sort of guess this prefactor, and that will also work. It will be limited to what your guesses are for the prefactor. There are some models which I haven't explored. So you don't have to actually tabulate all of this from MD simulation. You can do it in a few other ways. Other questions?
So with your multiple runs, you were showing that you were getting some different results.
Mm-hmm.
So by the end of the simulation, does it converge? Like all the results converge?
Converge, okay, yeah, that's a good question. So converge in the sense of what is we can calculate error bar from this. In this particular case, the error bars were pretty small, but yeah, that is a good point. You can have situations where you have bigger error bars, meaning for the benefit of everyone, like you run it 100 times, and how different is the configuration, let's say the particle size distribution every time you run. I don't have that plot, but in the publication we do definitely have it. You can check it out. In our case, the error bar was pretty small.
So because we use grand canonical Monte Carlo, and by the end of the simulation, we see that all the results converge towards.
You do use grand canonical Monte Carlo for what, surface absorption?
No, sir, for segregation, to understand segregation.
Okay.
Of solute.
Oh, that's good. That's good. What sort of method do you use for grand canonical Monte Carlo? Okay.
Yes.
So I'm just curious, what software do you use? LAMPS. Okay. There is also very popular software developed out of the University of Minnesota by Ilya Sipman. That is, I don't recall the name at the moment, but that is another grand canonical Monte Carlo solver. Yeah. If you want to keep the chemical potential fixed for a process, then that's the only method you have out there.
So the trick is getting physics in your probability equation.
Yeah.
I mean, that's the trick.
Right.
So
And it's limited
otherwise
to.
you can kind of prescribe whatever rate you want.
And if what you have tabulated is very limited what you're going to get out of it is not going to be physically meaningful, right? So it's very important to be able to compare with some sort of a experimental data surface characterization. But this is a neat tool. I mean, there is certainly ways of improving it, but yeah, what are the events occurring? And you have to consider at least the frequent events. Okay, now let's move to a different example, which is actually a bit more challenging, but chronologically, that was the first model we kind of developed before this on lattice. By the way, just concluding from this, the key things that we found are we were able to look at growth of films, look at growth rates and the morphology. A couple of things that were related that I have already presented here that we found is what are the electronic properties of the interface that you get in the film. And while I'm not presenting here, we have looked at it, the band structure of the interface of the PCBM and perovskite. It's a complex system. So that's kind of the follow-up of this, something that we have done, but I'm not presenting here. But one of the things that I mentioned is this: in the stock solution, we looked at different concentration, and agglomeration of these particles in the stock solution is a big deal. We've done some work looking at just at molecular dynamics level, different solvents, toluene, indene, and mixtures of solvents. And what we have noticed, you can tune it quite a bit because it depends on how polar your solvent is, and if it's an aromatic solvent as well, for example, toluene or indene. So it has an aromatic ring. You can tune the solubility of these particles and tune the particle size distribution. And if you do that, if you have dispersed particles, then it's more likely that you have a more uniformly grown film. And if you have a uniformly grown film, then you will have pathways for electron conduction, which is basically the purpose of this film that you're trying to develop, the electron transport layer. So to that point, it's important to model the shape and size of agglomerating particles in a solvent medium. Okay, this is not just related to this particular application. There are many applications of the shape and structure of colloidal suspensions when you're having agglomeration processes in a solvated environment. And sampling is pretty limited for those systems if you're doing calculations at molecular dynamics level, because you're only limited to sampling, let's say, 100 particles. If these are molecular particles, we're talking about molecules such as PCBMs or fullerenes. So it's also important to be able to scale these agglomeration processes with some methodology. So we developed our own code to look at this evolving system, kind of a colloidal system with kinetic Monte Carlo. But as opposed to the crystal growth, which happens at certain specific site, this is an off-lattice system, right? So let me present this next. Do we want to take a short break? Come back? Oh, POTS. That's another model that is available on SPARCs.
I've never really done kinetic. I've been in projects where they do kinetic, but they just show
really?
results, and I'm like, how do you get time to do this stuff?
So for what sort of systems do they use? For lattice dynamics?
Ring growth, this kind of things, phase evolution, this kind of stuff. So
I wonder where they get the inputs from. Maybe they just get all those energies for those processes and then use a prefactor. That's the usual stuff. You guess the prefactor, the frequencies of barrier crossing. That part is.
To simulate precipitation, then what will be the input for kinetic Monte Carlo simulation?
similar, right? I mean, you have to look at the energies for each of those processes. Okay. Okay, let's start from where we left, looking at an off-site kinetic Monte Carlo model for particle growth, and also looking at the evolution of its shape and fractal dimension. So how do we get started? Once again, I will quickly show you the algorithm here. I think I have a little more details for this one. So you start out by determining all the possible processes for how this particle will grow in the system, and how frequently each of, basically listing out all the events and how frequently they occur, from which you come up with a cumulative transition rate function that you can stochastically pick events to occur and then evolve it as the particle grows, and you kind of update the clock to have a sense of how long, what time interval for that process is, and getting a time scale for the process that way. This is kind of, so there are two aspects. This is the general algorithm, right? But one of the key steps is here, this one here. How do you come up with a classification algorithm for these events to measure their rates or calculate their rates? And then the other piece that is important is, once you have that classification algorithm, especially for off-lattice kinetic Monte Carlo, how do you kind of make that process happen? In case of on lattice, there is a particular crystal site that you want to, let's say, deposit an atom, right, or a molecule, and you want a certain neighborhood. Let's say there are one neighboring PCBM in the x direction, two in the diagonal direction. So it's a matter of scanning that surface and identifying a spot for this process to happen. That process is a bit more challenging when you're doing it off lattice. Okay, so how do we do that? So in this system, first of all, what system did we employ it for? So we came up with a somewhat simpler structure than in the previous system, because this is off lattice. This was just fullerene, which is a icosahedral C60 molecule, right? We were interested in looking at the aggregation mechanism for C60 in a solvated environment, which is basically a water with sodium chloride solution. So we looked at a couple of different salt solutions. In real life, a lot of colloidal processes happen that way. I mean, aggregation processes with salt environment, salt solution. The typical concentrations is fairly low, but because we are looking at a molecular dynamics simulation, we can't really, if we look at super low concentration, we simply cannot model it in a feasible way, given the computational like the time it takes for those systems, for super large systems. So we look at an elevated concentration in our system. So let me skip this slide. So let me show you an example of the type of process that happens during this colloidal particle growth. So you, let's say, have a trimer of 3 fullerenes in a solvated phase, and there is a dimer that is in the neighborhood, and then they interact and form an agglomerated phase. So the question is, how do we define a process that is this way? It's a lot more complex, right? So we came up with a description. There are many ways you can, again, come up with a classification and description of the individual processes. One of them, at a very elemental level, is, let's say, all I care about is the size of this agglomerate. So I can just think about, well, there is a trimer that is aggregating with a dimer, and we have a 5-member or pentamer, if you want to call it that, cluster, right? So if you do that, that makes it pretty simple, and you can continue to grow your cluster just based on 2 particles that agglomerate depending on its size. But what you won't capture that way is the shape. All trimers and dimers don't necessarily aggregate the same way. There are many different, infinitely large, different types of configurations that could happen. So on the one hand, the simplest model would be just to look at the size. The other hand, it's an untenable problem if you want to evaluate all possible configurations. But if you just wanted to keep some sort of a shape information intact, maybe you can look at the exact site where that event is happening, in this case, this particle 2, right, and its coordination environment. So in this case, this is a trimer, meaning this particle, this molecule, the fullerene 2, has 2 neighboring fullerenes, right? It's a trimer, but this particular site has 2 neighbors. On the other hand, the dimer that is kind of clustering with it, that particular site, its neighbor, has only 1 neighboring fullerene. So, can we somehow keep this information intact? So, to do that, we come up with 3 variables and define a vector to keep track of the nature of the event. The first variable is S, which is basically the size of the cluster with which this addition process is happening, right? We call this the seed fullerene, by the way. This, let's say, call it particle A. This is a seed fullerene, and this particle B, which is the added fullerene cluster. Okay. So, we want to keep track of the size of the cluster that is aggregating and the number of nearest neighbors for A, the seed fullerene, and the added fullerene, Ni, Nj. So, if we come up with a list, if we classify each event that we observe from molecular dynamics in that fashion, then we can come up with a comprehensive list and look at shape evolution as well. So, this one is S2, this one is Ni equals 2, and this one is Ni equals 1. Let me kind of erase this for clarification. So, again, this is the size of the added cluster 2, the number of nearest neighbors of the site, the seed fullerene that where the addition is happening is 2, and the number of nearest neighbors of the added cluster is 1. So, how do we get these rates, right? We have to do some sort of calculation or experiments. In this case, again, like in the previous case, we ran MD simulations, but because the shape of the fullerene is simpler than PCBM, we were able to come up with a coarse grain model. So, the Martini force field has a coarse grain model for fullerenes, and Martini force field has a coarse grain model for solvents like water. So, coarse grain model allows you to kind of combine multiple molecules a lot of times into single clusters. For example, solvents like water, for Martini force field, there are clusters of 4 water molecules. So, instead of dealing with 4 times 3, 12 atoms for which you are actually explicitly calculating the dynamics, you have only 1 bead, which is like a 1 atom, you can think of it that way, right? Same with fullerene. Instead of dealing with a C60 molecule, 60 atoms for which you really don't need to care about the dynamics as far as this agglomeration process is concerned, you can deal with it as a single particle or single bead. So, this one involves coarse grain molecular dynamics, which can really increase the number of, do I have the number of atoms that I modeled? Let us see with this coarse grain MD. I think it was more than 2 million if you counted the number of atoms for the system that we were able to look at with the coarse grain molecular dynamics for this particular case. Okay. So, again, you saw that chart in terms of the steps for this individual process. You know, the first step is to randomly choose an initial seed cluster and evolve it, right. So, we develop a library of clusters from our coarse grain molecular dynamics. Just looking at the configurations, we can store the different configurations of the clusters. We were able to store a couple of millions of different cluster configurations. So, it is like a library of different clusters that are available to merge and agglomerate with the specific fullerene aggregate that you are trying to grow, right. Once you choose the cluster, you calculate the description of it, of each of the fullerene atoms in this configuration. So, let us say you have chosen this cluster, right. It is classified as 2, 2 and 2, right. On the other hand, if this cluster was something like this, let me show you a different example, right. It is a cluster of size 3, but what is the description of each of the fullerene atom here? This one is 1, 2, 1, because the ones on the left and the right have only 1 neighbor, and the one at the center has 2 neighbors. So, this kind of again has some information associated with the shape or packing of the particle itself. So, you classify that, and how do you determine that an agglomeration event is happening from the MD simulation? Obviously, you have to have a cutoff distance. When 2 neighboring fullerene particles are within a certain cutoff distance based on their distance of the center of mass, you can associate it with an agglomeration event. This one, fortunately, is determined based on the kind of the van der Waals radius, if you want to call it that, of fullerene itself. So, it is pretty straightforward. We did a sensitivity study of this as well with our MD. So, we choose a cutoff distance of 1.15 nanometer between the centers of mass of two neighboring fullerenes to say that, well, these are in a cluster. Now, you have to choose one of the events from the event table, and I think I have an example of the event table in a couple of slides. So, maybe I'll move forward, that might be easier. Okay, so let's say this is an event table, simplified. Obviously, our event collection of events was a lot more extensive than this. So, you have a quatromer, or like a collection of 4 particles, and each particle has a descriptor of number of nearest neighbors. And here you have a list of events that can happen, right? These events are just numbered sequentially 1 through 6 in this example. And in the first event, you have a cluster of size 4 that attaches to one of the fullerenes here. Remember, I determined this, named the coordination number of the seed fullerene as Ni. So, the first event is you identify a fullerene in this cluster that has a nearest number of neighbors 1, and then you attach a fullerene from this cluster which also has a nearest number of neighbor 1, right. So, you search the library for all clusters of size 4 that you have accumulated in your database and identify the right size and an atom in there, or a molecule in there of fullerene that has the right number of nearest neighbors. But it so happens this is not going to be a possible event. It is kind of a impossible event in this case, because none of these fullerenes have a nearest number of neighbor of 1. So, it is kind of, we check it out. So, in fact, the first and the last event here are not feasible. The last one had NIE4, and the only 2 options we have in this case are 2 and 3. So, we kind of cross these 2 out. Let me use my eraser, because these are not going to be feasible. And now we have an option of these 4 events. Each of them have a certain rate constant or transition rate. So, this is the part where we use our stochastic approach of generating a random number based on which we determine which particular event is going to happen. So, let us for example say that this first event is what we pick from this table. So, what is the definition of this first event? That we pick a site which has 3 neighbors. So, we have 2 options here, and then we pick a cluster of size 2, a dimer from our library, and in a dimer it is pretty straightforward. Anyways, in a dimer, what is the nearest number of neighbors that can happen? It has got to be 1 and 1, right. So, we take a dimer and attach it to either this site or this site, the ones with 3, right. So, in this example, let us say this is what we do, okay. But there is a problem. How do we achieve this? There are many different configurations for doing this, right. We can attach it like this, we can attach it like this, or we can even have a situation where it kind of overlaps one of the fullerenes with one of the existing fullerenes of the cluster. Remember, this is an off lattice, so orientation is at play. You just take the coordinates of this and attach it, but you do not know where you land. Have you landed in a configuration where you are overlapping? That is obviously physically not meaningful if that happens. So, there can be overlaps that result from this. So, something like this. So, now how do you get rid of the overlap? You can perform a static energy minimization to make sure you kind of correct for that, energetically non-feasible, energetic configuration that is not going to be feasible in this case. Okay. So, that is the algorithm. So, the kinetic Monte Carlo has to have an energy minimization built into it, because this is off lattice. That is pretty important. Okay. I will go back now a couple of slides. I think the order was kind of messed up. So, we start with an initial system of fullerene in distribution, particle distribution in the coarse grained simulation. So, this is the initial distribution that we modeled with our coarse grained molecular dynamics, and for the sake of completion I will just put this out there. We have to come up with an expression for these transition rates, and this was the specific expression we used for this particular example here. The coarse grained molecular dynamics was run with a much greater time step, because it's coarse grained, you are able to look at, use a much, that's one of the advantages of a coarse grained MD for this simplistic system. So, we were able to collect, as it says here, 1.5 million frames in this, right. So, this is pretty exhaustive sampling, that always helps. Okay. So, we corrected it. Yeah.
What is 1.5 million? So why minus 1?
Where? Oh, in here? That's a good question. So, why are we summing with f minus 1? Okay. I believe it is not counting the initial structure, probably. Yeah.
Those are the intervals. So
Right.
that's why.
Yeah, the number of intervals is, you know, if you have f frames, that's right. The number of intervals you have is 1 minus, right? That's correct. So, again, I mean, you start with an initial distribution with a library of clusters that you have assembled from your MD simulation. Okay. So, this is a snapshot of what we are trying to achieve here. Okay. So, we are trying to track the growth of each particle that we start with, which is itself a cluster, and through this kinetic Monte Carlo algorithm, we are going to grow it and come up with something either that can look like this, or we can have a shape which is more spherical, or we can have a shape that is 2D. Depending on the chemistry, you can have, you know, that is again tied to the precise simulation with the coarse grained molecular dynamics. So, depending on what sort of interaction you can have many different shapes. This is just an example. And essentially, this is at the coarse grain level, but if you think of it from an atomistic perspective, each of these particles has the chemistry of fullerene, which is captured from the molecular dynamics simulation. So, you are capturing the underlying physics at the atomistic or coarse grain scale, and then advancing it at a much coarser level with the Monte Carlo simulation. So, there are many things that we can determine from this and from analyzing the growth of these clusters. For example, this one again shows the number of fullerenes in the cluster with time, and you can go to as high as you can see 20,000 or more fullerene particles that are forming the cluster, which will not be feasible just simply because of the number of atoms you would have in molecular dynamics. 20,000 would mean 20,000 times 60, and the mole fraction of weight fraction of the concentration of fullerene in the solution was 7% by weight. So, if this is the number of atoms in the fullerene, now if you account for all the solvent, you are talking about tens of millions of, you know, atoms in the system, which MD simulations can't really access. So, what we saw is, you know, we modeled a few different systems. All these three are 7% weight percent fullerene, okay, in solutions with different salt concentration. The growth rate with time is nonlinear, which is kind of expected because you start out with fewer sites where these addition events can happen. As the cluster keeps growing, you have more number of accessible sites. It depends a little bit on the shape of the cluster though, how it's packed. If it's packed in a compact manner like a near spherical, then you have fewer sites available. On the other hand, if it's kind of branched off, then you have many more sites where these addition reactions or clustering reactions can happen. So, therefore, it's very important not only to know what the size is, but you also have to keep track of the shape and fractal dimension, which I'll present in a few minutes. So, the largest dimension that we modeled with our kinetic Monte Carlo was about 80 nanometer for this cluster. So, it's, you know, as it says here, 115 times the diameter of a single fullerene. So, it's pretty large if you're thinking of it from an atomistic perspective. With higher fullerene concentration, so this one here is 3.5 weight percent fullerene. Obviously, the kinetics is a lot slower for that lower concentration of fullerene shown by the red curve. Why do we have all these kind of scatter instead of having a single kind of a line, because again we are running this code many different times to come up with the evolution of this, right? It's Monte Carlo code. Okay, so to capture one aspect of how the cluster is distributed, whether it's more like a 2D or it's like a compact spherical shape, we calculated the radius of gyration. And I hesitate to call it the radius of gyration because we don't have rotational motion that is associated with this cluster. But in polymer community, it's pretty standard to use this expression to kind of see the distribution of a chain or a structure around its center of mass. So basically what you're capturing is how far you are at from the center of mass of this cluster. For each of the molecule, each of the fullerene in the cluster, you kind of are running the calculation for how far you are at from the center of mass. That way you're capturing some sort of a feel for the distribution of in this cluster, whether it's compact or kind of spread out. You can plot the radius of gyration with this number of steps that you're running in this algorithm, which gives you a sort of nonlinear change in the radius of this gyration with the steps. So then you think of, why is that the case? I mean, why do we start out with a very rapid change in the radius of gyration, and then after a while it kind of flattens out? That has to do with the sites that you are defining where these clustering processes are happening. At the beginning, like I said, you have very few sites where these will happen. As you branch out, remember in your original table, there are going to be some events. So you see there is an order of magnitude difference between the transition rate constant for this event 1. This is just a random example. It's not like we are taking the realistic rates from our table, but you can have a couple of orders of magnitude difference between the transition rates of individual events that you kind of see from that table, right? Maybe at the beginning you only had the option to choose events which were rather rare because you had their transition rates were rare, but you didn't have option, to select ones that are more common because there were just simply no sites where that attachment can happen. So you have a factor of 2, right? You need to have those sites accessible where those additions will happen, and then only then can you choose that particular event. Like we kind of ruled out the first 2 events simply because there was no specific location for the seed fullerene for that type of growth event to happen. So it's pretty complicated at the beginning, therefore you have a kind of slower growth or rapid growth, and then gradually it kind of flattens out. So in the colloidal community, one of the key physics question that you care about is, what is the regime for this agglomeration process? What is the limitation? I mean, what limits the rate of aggregation? And there are essentially 4 different regimes. One is diffusion limited cluster aggregation, so where the growth rate is only limited by the rate at which these particles are diffusing and coming in contact with each other. What it means is there is very little energy barrier for the clustering to happen. As soon as 2 particles kind of come in close contact, they collide and cluster up. On the other hand, there can be a regime which is reaction limited for this cluster aggregation, where you have a high energy barrier. Could be because these particles are charged and there is a repulsive force between these particles. By the way, the fullerene particles do have a slight negative charge. It's not a very strong negative charge, so they do have a little bit of a Coulombic repulsion, but they have a strong pi-pi interactions of these rings that are present in the icosahedral structure. So there's a combination, but there could be other nanoparticles that are somewhat negatively charged where it will be reaction limited, right? And then finally there is percolation and gelation, where there is very rapid agglomeration regime. Okay, how do you know what regime you are at in your agglomeration process? Typically there is a scaling law where you kind of scale between, you can fit this power law between the particle, the agglomerate size or cluster size and the radius of that gyration raised to a certain exponent or a certain power, right? And that is df, which is widely known as the fractal dimension of this cluster. Have you heard of fractal? Fractal is basically a shape, and it's branched out. It kind of is recursive. It repeats itself in many different ways, right? So it's kind of a descriptor of the shape, but in this case, it's a good estimate of the regime for this aggregation event. So we can therefore do this pretty effectively. We can take our model, look at the radius of gyration and the size, and then as the particle evolves in its size, we can fit this power law sort of fit and come up with a calculation for the fractal dimension, right, which will give us a good idea of what regime we are located at. Now, physically speaking, at very low salt concentration, even lower than 0.01, let's say 0.0001, typically for these particles, the aggregation transitions from RLCA to DLCA. But in our systems, we haven't really looked at that sort of low concentration. And also our fullerene concentration is 7-8%, which is pretty high. Deliberately, we wanted to have it as a high concentration because we wanted to, in a short time scale, to develop this model, see a lot of aggregation event. If we had a system where there was no aggregation happening because of a huge energy barrier, we won't be able to sample, right? That would be one of the limitations. So what we expect is we are not at RLCA because the energy barrier is pretty low for our system. So we expect at least DLCA or percolation as far as the regime for this aggregation process is concerned. So from this fit, okay, we come up with fractal dimensions that are distinct depending on the phase of the aggregation process. So you see, it's difficult to see here, but you see 3 different slopes, and those slopes are actually quite different. So the first one has a fit of 1.9 as the fractal dimension is concerned. So if you fit this 1.9 exponent with the size of the cluster, you get, it's not a perfect fit, there is some scatter. So R square is 0.9. It's difficult to have a very, very good fit for this case, but 1.9 falls under DLCA. This has been observed for not just fullerene, but gold, silica, polystyrene particles that agglomerate. Typically in the DLCA regime, the measured or analyzed fractal dimensions are between 1.5 to 1.9. So this is about DLCA regime, which is kind of expected for our system. The next one is the second piece of this at slightly larger sizes of agglomerate in here. It's kind of a transition phase, frankly, because it's a smaller domain here. The fitted, this one fits pretty well. The fitted exponent is 2.5. So 2.5 is well known to be on the percolated cluster regime. So there's a percolation process for the clustering to happen here. And then finally, for large clusters in our system, the biggest clusters we have, the fitted exponent is 3.0. Again, the fit is very good here, and it's certainly at the gelation regime for this colloidal particle to cluster at this point. Okay. So basically what we are doing is we are trying to identify the nature of the physics of the aggregation process, the size and the rate at which it grows, and also the shape that is captured from the radius of gyration. Questions? I'll just take a quick short break to see if there are any questions.
What the difference between percolation and dilation? What difference? Both of them become we have different size of the cluster.
The size of the cluster in this case, but in general, the aggregation rate is very different when you see these processes, and also gelation versus percolation regime leads to slightly different colloidal shape when they agglomerate in that fashion. Okay, so it's.
Then it will come in different system. Percolation will come in different system, and dilation will come in some other system.
Right. So it depends on the chemistry. So like I say, this model is fairly generic, that it's kind of capturing all these phases with fullerene, but you can easily take, instead of fullerene, a gold nanoparticle or something else that you're interested in dispersing in a solvent, or aggregating. In fact, one of the things that might be of interest in here is looking at this process happening in a gaseous phase in air, or you could get into sintering processes, any kind of clustering process that you might be interested in, with the modification that you have to first model the chemistry, which will be very different depending on the chemical system you are interested in, the phase, the solvation phase. If you have a liquid solvent, is it polar, non-polar, aromatic? So those things will completely change this mechanism at play here. We were interested to see that in the range of salt concentrations that we are interested in, fundamentally the growth rates are different, but the shape and the structure of these growing cluster, are they different? So to do that, we normalized these parameters, the radius of gyration and the cluster size. So how do you normalize against what? So we kind of chose, so if you are looking at this regime, we normalized with respect to somewhat of a typical RG and N value, right, at the end of that particular DLCA regime, and normalize RG with, let's say this is RG prime and this is N prime, okay, and plotted it. Okay, so this is a normalized plot. The interesting aspect is if we normalize it, all these fall on top of each other, which kind of suggests that in terms of the aggregation process or clustering process, the physics is pretty similar. The salt concentration is not really playing a huge role here. Okay. In this community, the other a very popular model that is used quite often from Witten and Sander is you can come up with like a time scale for if you know the size of the cluster, and if you can come up with an expression for the growth rate of the cluster with respect to the current size and its fractal dimension. Okay, so in our case, we already have the cluster size and the fractal dimension that we have characterized here. So we wanted to see whether the kinetic Monte Carlo, the time that is estimated from the kinetic Monte Carlo, actually agrees with the size of the cluster and the fractal dimension. So we are kind of doing a reverse process of plotting this n raised to df minus 1 over d from this general rate equation. If we know the fractal dimension, does it fit? And the fit in these curves is pretty good. So it kind of agrees with this sort of empirical law. This is not really a very quantitative validation, but it's just a qualitative validation of our model. So we came up with this off-lattice Monte Carlo model to be able to kind of predict the growth of a cluster of molecules in this case, but could be atoms or other nanoparticles in a solvated environment in our case, and track its growth rate, the growth clustering regime or physics of the clustering process, and its shape and size distribution. We could run this essentially in this bath of this clustering regime. We can run this calculation for various starting configurations and distributions that you can characterize experimentally through a particle zeta size or some sort of an experimental characterization. You can get a particle size distribution, and we can use this model to see time evolution of that particle size distribution in various chemical environments. So I would say that it's pretty generic in that sense. Questions? Like I mentioned, this is an example of a couple of different flavors of kinetic Monte Carlo, but you're not limited to that. There are many different models you can run also for crystalline systems using software such as SPARC, but there are other software and codes available, I'm sure. So Dave, you mentioned you use, or your collaborators use these codes. Is it SPARC or some other codes? Okay.
KMC is always it.
Okay. So there are, I believe, some open source codes available if you are interested in this. You don't have to start from scratch unless, I believe, if it's off lattice, there might not be too many options, but if it's on lattice system, then there could be codes that you can adapt. The key challenge again is to tabulate those list of events and find their transition rates. This has been used very successfully recently as an update in the pharmaceutical industry. There is a group at ETH Zurich, Stefano Piana. They were one of the pioneers of this method, but recently they kind of used it for crystal growth for pharmaceutical systems like drugs. and they got some very good agreements. And their approach does not necessarily use molecular dynamics to specify the rates. They have a different way of characterizing it, as far as I remember. But yeah.
Starting variable is number of particles, initial number of particles.
Yeah, you can start with a distribution, and you can take each particle from that distribution and model its growth, growth process. And then if you do this 10 times, you can see, because this is a stochastic process and off lattice, the final structure that will grow out will look very different. So you have to sample as many of this as possible, and and come up with some sort of an analysis. There will be a distribution for both the size of the particle as well as the shape.
Capital N is the cluster size.
In this case, it's the current size of the cluster. And where it goes, what its shape is going to be next is governed by this general law used in the colloidal community. It has to do with the fractal dimension and the radius of gyration of that particular structure at that point.
So fractal dimension can be measured.
Fractal dimension can be measured, so you can characterize a particle in a colloidal system and run some measurements. I'm not an experimentalist, but I'm thinking it should be straightforward to characterize particle shapes and structures from a system.
Yeah, it's used to describe grain shapes in polycrystals a lot of times. Fractal dimension and how it evolves.
I'm interested in extending this to other processes, like I mentioned, perhaps sintering, but then there is an additional situation where this is a system of spheres, almost like, you can call it either a hard sphere or a soft sphere. At the MD level, it's a soft sphere. Let's call it a soft sphere. But if you have sintering, obviously one of the key things is, due to the thermal energy, there will be change there will be diffusion, there will be deformation of these particles, which is certainly not considered here, which will be important that you have to consider for a sintering process.
In case of liquid phase sintering, then this deformation will be much more higher as expected from the theoretical calculations.
Right. These calculations, but deformation is something that is not accounted.
In this case, the deformation has not been
No deformation.
Not at all.
Not at all. To the extent that this is based out of a coarse grain potential model that is a soft sphere model. But the cluster that is growing, the only energetic function, treatment that we do is the energy minimization, a very short energy minimization to remove overlap to that extent. So the code here that we developed has many modules. Actually, it's not one single code. There is one code that, obviously this is MD simulation, but one code just analyzes the output from the MD to come up with a library of those clusters and classification of the clusters, including the coordination environment of each particle in that cluster. And then there is a separate code for the kinetic Monte Carlo as well, which is actually the simpler of the two. And then in the kinetic Monte Carlo, the most intense module, more complex module is where you kind of select one cluster from the library and attach it to the right location. And even for that, something that I didn't mention, you can have multiple seed fullerene in a certain cluster that you have picked, which has a coordination number of 3. So you have to kind of randomly pick either this or this one here in this case. Yeah.
So you are saying about the cluster. So how much number of atoms will be there in a particular cluster? Like you are having some number.
So which cluster? The one that we are getting from the coarse grain molecular dynamics, or for that one, I think we had, let me just quickly look up to give you an exact number. As far as I remember, it was of the order of 2000 fullerene molecule. Yeah, but is that what you're asking, or the kinetic Monte Carlo?
Both the cases.
Okay. So with the MD, like I mentioned, it was, I'm just looking at the paper, I don't quite remember the exact number here. Give me a moment. Okay. We had coarse grain molecular dynamics. Yeah, I think it's about 2000. But with the Monte Carlo, we generated structures with up to 30,000 of these particles. But one of the things is we didn't have, one of the things that is also important is where do you end this process, clustering process, which is a little challenging. It's not very straightforward, because in the real system, the molecular dynamics that you're using for getting all these rates, it's still limited to a much smaller system, right? And its concentration is depleting. So as the clustering event happens, it's an NVT ensemble. So the total number of fullerenes is constant, while the kinetic Monte Carlo is not limited that way, which is both an advantage because you can sample to much larger systems, but really where you end this sampling process and say, okay, this is the extent to which it will grow is something to be thought about. And I think that's where comparing it with some experimental measurements would be handy.
We can use this approach to tell about the solidification also. So it's like we have liquid and how the crystals are growing.
I think certainly. I think there would certainly be some. So one thing to look at would be the, let me see, I might have SPARC's open here. So this is the SPARC's code, and you can see my screen. It has many different modules. It has a sintering model actually, so I haven't explored it, but if you're interested in sintering process, this would be something to look at. It has a diffusion model.
So this sintering model can predict the time as well. Like suppose we.
I think so. I'm pretty confident it will predict the time.
Solid phase sintering or liquid phase sintering. So we just input the type of sintering
Mm-hmm.
and the temperature at which we want to do the sintering. So
Right.
we can give the time value as well, sir, as an output.
Yes, if it works, then there will certainly be a time scale that will be outputted from the code. But like I said, I haven't run the SPARC's sintering model. They advertise it to be in here, so something to try out if you're interested in that.
This is sir open source and we can run it in.
Yeah, it's
Quantum
certainly open source. You can run it where?
In sir Quantum Espresso or
Quantum Espresso, that's a different code, DFT code. So you want to combine these?
combined, yes.
Yes, it is possible, perhaps. For example, that at the beginning of my lecture, I showed you an example of a soot particle growth. If I remember correctly, in it, there was Monte Carlo, but there was also some DFT-based energy minimization as the particle was growing. So yeah, you can certainly combine modules. That's a good thought. It's how simple it will be is something you'd have to explore. Yeah.
Just while explaining the electronic properties of a material, so in case of doping, we usually have very less number of the dopants in the structure. So ideally, if we go for the DFT and low atomic level calculations, so we will not be considering
Dilute systems.
Yes, dilute systems. So we will not be considering a large supercell or something like that. So we are not considering large number of atoms. Can we somehow explain the electronic behavior using this Monte Carlo? But actually we are not. I don't think we are getting this band structure and other things from this.
No, it certainly doesn't have a quantum level resolution. That's where, like you suggested, you will have to combine this in some shape or form with a DFT code, which I can think about. I can think of that. At least theoretically, it should be possible, right? You're running this code to evolve the system at a non-quantum level to the next event, let's say, and then you're running a DFT minimization. So that should be possible. That's what is done in ab initio molecular dynamics, right? You separate out the nuclear dynamics from the electronic properties. So you kind of evolve the nucleus in a classical Newtonian dynamics like MD, while every step you're running a DFT solver to get the electronic structure and minimizing the energy. So why not, you should be able to do that here as well. But the code aspects of it, there are many different things here, whether the codes are compatible. But in principle, you should be able to create a script to call this. If not anything else, if you cannot integrate the codes themselves, you can develop a script that runs a few iterations of this, and then it runs a DFT. But if you are scaling up, that's the challenge, right? With DFT, you can't handle large systems. Then you will have to be restricted to smaller systems. And just look at rare events, maybe, with high energy barrier.
One more case is like designing the heterostructures.
Mm-hmm.
We have different materials and we want to understand the role of interfaces.
Okay.
So in that case also DFT, like we can do that in the DFT also.
Interfaces are challenging, especially hetero interfaces.
Yes, then it's a bit challenging. So can we do that thing also here in this one? No. For that I think molecular dynamics will be better approach.
What do you want to achieve?
Sir,
What's your goal?
I want to see that whether this which type of heterojunctions are forming at the if we have a material like P type and N type.
Mm-hmm.
So how the bands are aligning at the interface. So is it bending is there or not?
So that is typically within the domain of DFT.
Okay.
Kinetic Monte Carlo and Monte Carlo are different, right? I mean, kinetic Monte Carlo is a very specific flavor of it. Monte Carlo, on the other hand, is again a very different approach where you can use Monte Carlo in conjunction with DFT, right, to sample energy configurations. So I see that aspect more relevant than kinetic Monte Carlo, at least directly speaking, but I haven't thought of it. So good thought. Other questions?
So one question which we face in this Monte Carlo
Yeah, you're running grand canonical Monte Carlo, right?
So
Yeah.
what number of steps is at what step we should enter
Right.
simulation or?
So maybe a partial pressure if you're looking at a vapors phase or something where you know that this is the final partial pressure of that phase. A lot of people use it for gas absorption, and I know they do that. You have to set a criteria for ending the calculation, right? Yeah.
So we have situation specific solutions, but we don't have a broad solution for this problem.
I'll be interested to know a little bit more about your grand canonical Monte Carlo calculation. So let's chat. Okay, thank you for your attention. So I'm glad to see that there's some interest.